There is a machine that should be dead, still whispering to us from 14 billion miles away. Two spacecraft launched in 1977, built for a 5-year mission to photograph Jupiter and Saturn, then drift into silence like every probe before them. The engineers who built them expected fuel depletion, instrument failure, and the cold mathematical certainty that nothing lasts forever in the vacuum of space. That was 47 years ago. Voyager 1 and Voyager 2 are still transmitting, still functioning, still sending back data from a place no human eye will ever see and no telescope can properly image. They have crossed a boundary we didn't know the exact location of. They have measured a cosmic environment we fundamentally misunderstood. And they have revealed structures at the edge of our solar system that no model predicted and no theory cleanly explains. What they found out there has rewritten the map. The Heliopause, the place where our sun's influence ends and true interstellar space begins, turned out to be billions of miles farther than every scientific model suggested. A magnetic highway appeared in the data, a coherent structure funneling particles at impossible speeds through a region that was supposed to be empty and chaotic. The interstellar medium itself, the space between stars we thought was cold and thin, came back hot and dense and stranger than anyone anticipated. And then there were the tsunami waves. Solar storms launched from our sun's surface, racing outward past every planet, past the Heliopause, propagating like shockwaves through the galaxy itself. This is not the story of two robots floating quietly into the dark. This is the story of what happens when you send something farther than it was ever meant to go, and it refuses to stop talking. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. In the summer of 1977, humanity stood on the edge of the solar system and admitted something uncomfortable. We had no idea what was out there. Not really, not in any way that would satisfy a curious child asking questions at a planetarium. The outer planets, the giants beyond Mars, were little more than educated guesses wrapped in mathematics. Jupiter was a bright dot with stripes you could see through a backyard telescope if the seeing was good. Saturn had rings, everyone knew that much, though nobody could tell you precisely what they were made of or why they stayed put. Uranus and Neptune were just names attached to calculations, distant hypotheses holding down the far end of the solar system like bookends nobody had bothered to read. We had theories, sure, models built on centuries of observation, refined through decades of physics. But theories are just stories we tell ourselves about things we cannot touch. And in 1977, we could not touch anything beyond Mars. That summer, two spacecraft left Earth carrying instruments designed to change that. They were named Voyager 1 and Voyager 2, and they were built for a mission expected to last 5 years. 5 years to fly past Jupiter and Saturn, take pictures, measure magnetic fields, radio home, and then drift into the dark as silent monuments to human ambition. That was the plan, a 5-year mission, except nobody told the spacecraft. Voyager 2 launched first on August 20, 1977 from Cape Canaveral. Voyager 1 followed 16 days later on September 5. The naming convention was deliberate and slightly confusing. Voyager 1 was launched second but followed a faster trajectory, meaning it would arrive at Jupiter first. So the second spacecraft to leave Earth became Voyager 1 and the first became Voyager 2. NASA does not do anything without a reason. But sometimes the reasons make more sense to mission planners than to the rest of us. The launches themselves were not glamorous. No dramatic countdowns broadcast to millions. No president watching from the viewing stands. The Space Shuttle program was still 4 years away from its first flight, and public attention in 1977 was elsewhere. Star Wars had just opened in theaters. Elvis Presley died 3 days before Voyager 2 launched. The Cold War was grinding along. A pair of robot probes heading toward Jupiter did not move the needle on national consciousness the way Apollo had less than a decade earlier. But the people who built those probes, the engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, knew exactly what they were launching. They knew they were sending the most sophisticated machines humanity had ever built into a region of space where no machine had ever operated for long. And they knew, even if they did not say it out loud, that these spacecraft might be the only visitors those distant worlds would ever receive in their lifetimes. To understand why the Voyager missions happened when they did, you need to understand the alignment. Not a metaphorical alignment of political will or scientific ambition, though both were necessary. An actual alignment of planets. Every 175 years, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, arrange themselves in the sky in such a way that a single spacecraft launched from Earth can visit all 4 in sequence using a technique called gravity assist. Fly close to Jupiter. Let its gravity sling you toward Saturn. Fly close to Saturn. Let it fling you toward Uranus. Each planet acts as a stepping stone, bending your trajectory and accelerating you toward the next target without burning a drop of fuel. The physics had been worked out in the 1960s by a mathematician named Michael Minovich at JPL. The trajectory was so efficient it had a nickname among mission planners. They called it the Grand Tour. The last time the planets aligned this way, Thomas Jefferson was president. The next time it would happen, no one alive in 1977 would be around to see it. If NASA wanted to visit all 4 outer planets in a single mission, this was the window. Miss it, and you would have to wait until the 22nd century. The original proposal for the Grand Tour was ambitious to the point of fantasy. 4 spacecraft, 2 launched in 1977 and 2 more in 1979, visiting every outer planet and sending back data for a decade or more. The price tag was equally ambitious. Congress looked at the budget, looked at the Vietnam War still burning through federal money, looked at the recession and cut the mission in half. 2 spacecraft. 5-year primary mission. Jupiter and Saturn only. If the probes survived past that, great. If not, we got what we paid for. The engineers at JPL took the reduced budget and built something that would outlast everyone involved in the decision to cut it. Each Voyager spacecraft was about the size of a small car, roughly 800 kilograms fully fueled. The most recognizable feature was the high-gain antenna, a white dish 3.7 meters across that looked like a satellite TV receiver bolted to the side of a mechanical insect. Beneath the antenna, a cluster of instruments sprouted in every direction. Cameras, magnetometers, spectrometers, plasma detectors, cosmic ray sensors. 10 scientific instruments in total, each one designed to answer a specific question about the outer planets. What is the temperature of Jupiter's cloud tops? What is Saturn's magnetosphere made of? How thick are the rings? Do the moons have atmospheres? Are there volcanoes? Are there oceans? Power came from 3 radioisotope thermoelectric generators, or RTGs, mounted on a long boom extending out from the main body of the spacecraft. RTGs are about as simple as nuclear technology gets. Take a chunk of plutonium-238, let it decay naturally, and capture the heat it produces with thermocouples that convert temperature difference into electricity. no moving parts, no sunlight required. The plutonium in Voyager's RTGs was producing about 470 watts of power at launch, enough to run a few light bulbs. Over time, as the plutonium decayed, the power output would drop. The engineers calculated the RTGs would still be producing usable power for at least a decade, maybe longer if they got lucky. 50 years later, in 2027, Voyager 1 is still transmitting on less than 200 watts. The RTGs are still working. The engineers got more than lucky. Communication was always going to be the hardest part. At Jupiter's distance, roughly 5 astronomical units from Earth, radio signals take about 43 minutes to make a one-way trip. At Neptune, the delay stretches to over 4 hours. You cannot fly a spacecraft in real time across that gap. Every command sent from Earth has to be planned in advance, uploaded in sequence, and executed autonomously by the spacecraft's onboard computer. And that computer, by modern standards, was laughably primitive. 8-bit processor, 64 kilobytes of total memory, less computing power than a digital thermostat. The entire command and control system ran on software written in assembly language, hand-coded by programmers who had to think in terms of individual processor instructions because there was no room for anything else. One of the engineers later compared programming Voyager to writing poetry in a language with only 50 words. You could do it, but every word had to count. The cameras were the stars of the instrument package, at least as far as the public was concerned. 2 of them mounted on a scan platform that could rotate independently of the main spacecraft body. One was a narrow-angle camera with an 8-inch telescope for high-resolution images. The other was a wide-angle camera for context shots. Both used Vidicon tubes, a technology that in 1977 was already being phased out in favor of electronic sensors. But Vidicons were proven, reliable, and radiation-hardened. Nobody knew what the radiation environment around Jupiter would do to electronics. Better to fly something old and rugged than something new and fragile. The images those cameras sent back would take hours to transmit at a data rate of 160 bits per second. A single photograph required nearly 10 minutes to download. A modern smartphone sends data 1 million times faster, but in 1977, 160 bits per second across 500 million kilometers was a miracle. The scientific community in the late 70s did not expect much from the outer solar system because there was not much to expect based on what we could observe from Earth. Jupiter was known to have at least 13 moons, though some were barely visible and their orbits were poorly understood. The Great Red Spot, a massive storm in Jupiter's atmosphere, had been observed since the 1600s, but no one knew how deep it went or what powered it. Saturn's rings were beautiful through a telescope, but the structure and composition were mysteries. Were they solid, liquid, ice, rock, a continuous sheet, or billions of individual particles? No one could say for sure. Uranus and Neptune were even more obscure. Uranus had been discovered in 1781 by William Herschel, who initially thought it was a comet. Neptune was found in 1846 after mathematicians predicted its position based on irregularities in Uranus's orbit. Both planets were so faint and so far away that even the best telescopes on Earth could barely resolve them as disks. Any moons they had were speculative, any rings were theoretical. The only spacecraft that had ventured into the outer solar system before Voyager were Pioneer 10 and Pioneer 11, launched in 1972 and 1973. Pioneer 10 flew past Jupiter in December 1973 and sent back the first close-up images of the planet. Pioneer 11 followed a year later and then swung by Saturn in 1979. Both missions were successes, but both were also limited. The Pioneers carried fewer instruments than Voyager, their cameras were less capable, their data rates were slower, and neither spacecraft was designed to visit more than 2 planets. The Pioneers were scouts. Voyager was the expedition. The initial mission parameters were straightforward on paper. Launch in 1977, arrive at Jupiter in 1979. Spend a few months studying the planet and its moons, continue to Saturn, arrive in 1980 or 1981 depending on which spacecraft, study Saturn and its largest moon, Titan, which scientists suspected might have an atmosphere thick enough to hide a surface no telescope could see. After Saturn, the mission would be complete. The spacecraft would continue moving outward on trajectories that would eventually take them beyond the orbit of Pluto. But by that point, the instruments would likely be dead and the power would be too low to transmit. They would become derelict, coasting monuments to a bygone era of exploration, drifting silently through the space between stars for millions of years until gravity or a collision with something ended their journey. That was the expectation. A 5-year mission. A glorious 5 years, certainly, filled with discoveries and photographs that would rewrite textbooks. But still, 5 years. Then silence. The people who built Voyager did not talk much about what might happen after year 5. It felt presumptuous. Spacecraft do not survive indefinitely in deep space. Radiation degrades electronics, micrometeorites puncture fuel lines, components fail, systems shut down. The designers built in redundancy where they could back up systems for critical instruments, but there were limits to what you could do with 1970s technology and a fixed budget. The goal was to get to Saturn. Anything past that was a bonus, but they also did something strange. They built the spacecraft tougher than the mission required. The RTGs were rated for 10 years, but the plutonium half-life meant they would keep producing some power for decades. The attitude control thrusters carried enough fuel for far more course corrections than a 5-year mission needed. The communication system was designed to stay locked on Earth even as the spacecraft traveled billions of kilometers farther than Saturn. And the software, that hand-coded assembly language running on an 8-bit processor, was written with enough flexibility that mission controllers could reprogram the spacecraft in flight, uploading new instructions to compensate for failures or adapt to unexpected conditions. It was as if the engineers, even while telling themselves this was a 5-year mission, were quietly hedging their bets. Building a spacecraft that could survive longer just in case someone someday found a reason to keep it running. One of the most surprising aspects of the Voyager mission, at least in hindsight, was how little we knew about the hazards waiting beyond Mars. The radiation belts around Jupiter were expected to be intense, but no one knew how intense until Pioneer 10 flew through them and nearly got fried. Jupiter's magnetosphere, the region of space dominated by its magnetic field, turned out to be enormous, extending millions of kilometers into space, farther than anyone had predicted. If Voyager flew through the wrong part of that field at the wrong time, the electronics could be damaged beyond repair. The engineers planned the trajectory to minimize radiation exposure, threading the spacecraft through the safest corridors they could calculate, but it was educated guesswork. There were no maps, no previous missions to learn from except the Pioneers, and they had barely survived. The spacecraft were also flying into temperature extremes no Earth-based laboratory could fully replicate. Near Jupiter, sunlight is 27 times weaker than at Earth. Near Neptune, it is 900 times weaker. The cold alone could freeze lubricants, crack solder joints, and make metal brittle. The instruments had to work in an environment where the ambient temperature hovered around -200 degrees Celsius. Heaters kept the electronics warm, but those heaters drew power from the RTGs, and every watt spent on heating was a watt not available for science or communication. The mission planners ran endless simulations trying to balance power budgets, calculating how much heat each instrument needed, how long each could run per day, which systems could be shut down temporarily to save energy. It was a logistical puzzle with no margin for error. And then there was the question nobody wanted to ask out loud. What if the spacecraft found something we were not prepared to understand? The outer planets were blank canvases. Any observation, any measurement would be new data. But new data sometimes raises more questions than it answers. What if Jupiter's atmosphere was stranger than any model predicted? What if Saturn's rings defied every theory of orbital mechanics? What if one of the moons had an atmosphere, or volcanoes, or something even more unexpected? The instruments were designed to measure specific things, temperature, magnetic field strength, chemical composition, but they could not measure everything. There would be gaps, mysteries left unsolved, because the right instrument was not on board, or because the spacecraft flew past too quickly to get a second look. Carl Sagan, who would later become the public face of Voyager's cultural legacy, was deeply involved in the mission's planning. He understood better than most that Voyager was not just a scientific expedition, it was a statement, a declaration that humanity was capable of building machines that could travel farther than any human would ever go, at least in the foreseeable future, and send back knowledge from places we could only dream about. Sagan pushed for the inclusion of the Golden Record, a 12-inch gold-plated copper disc mounted on the side of each spacecraft carrying sounds and images from Earth. Music, greetings in 55 languages, photographs of people and places and things that represented the breadth of human experience. The idea was not that aliens would find it. The odds of that were vanishingly small. The idea was that we would know it was out there, a message in a bottle cast into the cosmic ocean, carrying a piece of us into eternity. The Golden Record was controversial. Some scientists thought it was a waste of mass that could have been used for instruments. Some engineers worried it would complicate the spacecraft's balance. Some politicians thought it was silly to send a record player into space when we could not even solve problems on Earth. But Sagan and his collaborators persisted, and NASA eventually agreed. The records were manufactured, mounted, and launched. And now, nearly 50 years later, those records are still out there, traveling farther from Earth every second, carrying Bach and Chuck Berry and the sound of a human heartbeat into a future none of us will live to see. When Voyager 1 and Voyager 2 left Earth in September 1977, they were state-of-the-art machines built by the best engineers and scientists NASA could assemble. They were also, by the standards of the mission's official parameters, disposable. 5 years, that was the window. After that, the universe would do what the universe does, and the spacecraft would either survive or they would not. Nobody at JPL in 1977 expected to still be talking to Voyager in 2027. Nobody expected the mission to outlast the careers of everyone who worked on it. Nobody expected a 5-year mission to become a 50-year mission with no end in sight. But that is exactly what happened, and the reason it happened starts with what Voyager found when it reached the outer planets, because the discoveries it made were not just data points to plug into models. They were revelations that forced scientists to reconsider everything they thought they knew about how the solar system worked. The first of those revelations came at Jupiter, and it did not take 5 years to realize that the official mission parameters had been, to put it mildly, optimistic. The edge of the solar system was not where anyone thought it was, and Voyager was about to prove it. Nobody knew where the solar system ended. That was the uncomfortable truth hanging over planetary science for most of the 20th century. We had drawn maps, sure. We had calculated orbits. We knew where the planets were. We knew roughly where the asteroid belt sat and where the Kuiper belt began, that disk of icy debris beyond Neptune where Pluto lived alongside thousands of other frozen bodies too small to qualify as proper planets. But beyond all that, where did the sun's influence actually stop? Where did the solar system, in any meaningful sense, give way to the rest of the galaxy? The answer depended entirely on what you meant by influence. Gravity was easy. The sun's gravitational pull extends theoretically to infinity, weakening with distance but never quite reaching zero. Anything orbiting the sun, no matter how far out, was still part of the solar system by that definition. But gravity alone did not capture what made the sun's neighborhood distinct from the interstellar void. The sun does more than pull on things. It blows. A constant hurricane of charged particles, electrons and protons mostly, streams outward from the sun's corona at speeds exceeding 1,000,000 miles per hour. This solar wind carries the sun's magnetic field with it, dragging loops and twists of magnetism out into space like invisible ribbons trailing behind a sprinter. That wind, that magnetic presence creates a bubble around the solar system, a region where the sun's particles and fields dominate over the thin gas drifting between the stars. That bubble has a name, the heliosphere, and the edge of that bubble, the place where the solar wind finally runs out of push and the interstellar medium starts pushing back, is called the Heliopause. The Heliopause is not a place you can visit in the way you visit a planet. It has no surface, no rocks, no temperature you could measure with a thermometer held out a window. It is a boundary defined purely by pressure. On one side, the solar wind is still stronger than the stuff between the stars. On the other side, the interstellar medium wins. Cross that line, and you are, by every reasonable definition, no longer inside the solar system. You are in interstellar space, the space between stars, the place where the rules change and the sun becomes just another distant point of light with no special authority over the particles around you. For decades, scientists assumed the Heliopause was somewhere out past the orbit of Pluto, maybe 80 or 90 times the distance from the Earth to the Sun. That distance unit, the Earth-Sun separation, is called an astronomical unit, or AU for short. 1 AU is about 93 million miles. Pluto orbits at roughly 40 AU. The predicted Heliopause sat around 85 to 90 AU, give or take. The models that produced those numbers were based on observations of the solar wind near Earth, measurements of how fast and how dense the wind was in our neighborhood, and assumptions about how much the wind would slow down and spread out as it traveled farther from the sun. The interstellar medium, the thin soup of hydrogen atoms and cosmic rays filling the space between stars, was harder to measure directly because we were sitting inside the heliosphere looking out. But astronomers could estimate its density and pressure based on observations of nearby stars and the way light from distant objects got absorbed or scattered by interstellar gas. Plug those numbers into the equations and the models spit out a boundary location. 85 AU seemed reasonable. Some models pushed it out to 90. A few optimistic estimates went as high as 100, but nobody was seriously predicting anything beyond that. The models also assumed the Heliopause would behave like a soap bubble. Smooth, spherical, maybe a little squashed on one side because the solar system is moving through the galaxy at about 50,000 miles per hour, and that motion would compress the bubble in the direction of travel like the bow wave on a boat. The upstream side, the direction the sun is heading, would be closer. The downstream side, the wake trailing behind, would stretch farther out. But overall, the picture was clean. The heliosphere was a protective bubble. The heliopause was its skin. The interstellar medium was everything outside. The models were elegant. The models were wrong. Voyager 1 reached the distance where the models predicted the heliopause should be in the mid-2000s, somewhere around 2005 or 2006, depending on which model you trusted. It kept going. No boundary, no sudden change in the solar wind. The instruments kept measuring the same kinds of particles they had been measuring for years. Solar wind protons, solar wind electrons. The magnetic field still pointed in directions consistent with the sun's influence. Whatever the heliopause was, Voyager had not found it yet. Mission scientists started quietly revising their estimates, maybe 95 AU, maybe 100. The spacecraft kept transmitting, the boundary kept retreating. By 2010, Voyager 1 was past 110 AU, farther from the Sun than any human-made object had ever traveled, and the data was starting to look strange. The solar wind was slowing down. Not gradually, the way you would expect as it lost energy traveling outward, but erratically. Some days the speed would drop. Other days it would spike back up. The density fluctuated wildly. The magnetic field twisted in directions that did not match the models. It was as if the spacecraft were flying through turbulence, a churning transition zone where the solar wind was fighting something it could not quite overpower. The scientists at JPL started calling this region the heliosheath, the outermost layer of the heliosphere, where the solar wind has slowed to subsonic speeds and is piling up against the pressure of the interstellar medium like water backing up behind a dam. The heliosheath was thicker and more chaotic than anyone had predicted. Voyager 1 spent years crossing it, transmitting data that made less sense the longer you stared at the graphs. Then, in the spring and summer of 2012, something shifted. The solar wind particle count started dropping, slowly at first, then faster. By late July, the detectors were registering less than half the number of solar wind protons they had been seeing a month earlier. At the same time, the cosmic ray count, particles arriving from outside the solar system, started climbing. Cosmic rays are high-energy particles, mostly protons, accelerated to nearly the speed of light by supernova explosions and other violent events in the galaxy. The heliosphere blocks most of them. The solar wind sweeps them aside the way a force field deflects bullets in a science fiction movie. If the cosmic ray count was going up, it meant the shield was weakening. Voyager was approaching the edge. On August 25th, 2012, the solar wind particle count dropped by 94% in a single day, not a gradual decline, a cliff. One day, the detectors were seeing a trickle of solar wind protons. The next day, almost nothing. At the same time, the cosmic ray flux spiked by nearly 10%. The spacecraft had crossed a boundary so sharp, it registered as a step function in the data. The heliopause, the edge of the solar system, the place where the sun's wind stops and the interstellar medium begins. Voyager 1 had found it, and it was not where anyone expected, 121 astronomical units from the sun, 18 billion miles, 2.4 billion miles farther than the most optimistic pre-Voyager models had predicted. The discrepancy was not a rounding error. It was not a small adjustment to account for measurement uncertainty. It was a fundamental mismatch between theory and reality. The heliosphere, the bubble of space carved out by the sun's wind, was vastly larger than the models said it should be. 30% larger in radius, which translated to more than twice the volume. If you had drawn a sphere around the solar system in 2011 based on the best available models, and then drawn the actual boundary where Voyager crossed, the difference would be impossible to ignore. The models were not close. They were wrong in a way that suggested something important was missing from our understanding of how the solar wind interacts with the galaxy. The announcement came in September 2013, more than a year after the crossing. NASA held a press conference. Scientists presented graphs showing the particle counts dropping and the cosmic ray counts rising. They explained that the boundary had been crossed, that Voyager 1 was now officially in interstellar space, the first human-made object to leave the solar system. The news made headlines around the world. Voyager had done it. After 35 years of flight, the spacecraft had crossed the final frontier and was now traveling through a region of space no probe had ever measured directly. The fact that the boundary was billions of miles farther out than expected got mentioned in the press releases, but it did not dominate the story the way it should have. The bigger shock, at least to the scientists analyzing the data, was not just where the Heliopause was, it was what it looked like up close. The models predicted a diffuse transition zone, a gradual blending of solar wind and interstellar medium over a distance of perhaps several AU. A slow fade from one environment to the other, like walking from a lit room into a dark hallway and waiting for your eyes to adjust. What Voyager found instead was a wall, not a physical wall, nothing solid, but a transition so abrupt that the particle counts changed by an order of magnitude in less than a day. The spacecraft was traveling at roughly 38,000 miles per hour, which meant it covered about 900,000 miles in 24 hours. Somewhere in that 900,000-mile span, the solar wind effectively vanished and the interstellar medium took over. That kind of sharpness implied something the models had not accounted for. The boundary was not static, it was dynamic, it moved, it flexed. It responded to changes in the solar wind pressure on one side and changes in the interstellar medium pressure on the other. And those changes could happen fast. Follow-up analysis showed that the Heliopause was not a smooth sphere at all. It was wrinkled, lumpy, porous in places. Magnetic fields on both sides of the boundary twisted and reconnected, opening temporary channels where particles could leak through. The data suggested that Voyager had crossed the boundary, then briefly dipped back into the heliosheath, then crossed again a few days later before finally settling into interstellar space for good. The crossing was not a single clean event. It was a series of back-and-forth transitions as the boundary rippled past the spacecraft like a curtain blowing in the wind. That rippling, that dynamic instability was completely absent from the pre-Voyager models. The heliosphere was not a neat protective bubble keeping the galaxy at bay. It was a turbulent, constantly shifting interface between two very different kinds of plasma, and the details of how that interface behaved depended on physics we were only beginning to understand. The immediate question was why? Why was the heliosphere so much larger than predicted? Several explanations surfaced almost immediately. One possibility was that the interstellar medium was less dense than astronomers had assumed. If the pressure pushing back against the solar wind was weaker, the solar wind could push farther out before stalling. Measurements from Voyager supported this idea to some extent. The density of neutral hydrogen atoms in the local interstellar medium turned out to be lower than earlier estimates, though not low enough to fully explain a 30% increase in the heliosphere's radius. Another possibility was that the solar wind itself was stronger or more persistent at large distances than the models predicted. Maybe the wind did not lose energy as quickly as we thought. Maybe magnetic fields carried some of the wind's momentum farther out than simple fluid dynamics would allow. The truth, as it usually is in these situations, was probably a combination of factors. The models had underestimated the size of the heliosphere because they had oversimplified both sides of the equation. The solar wind was more complex, the interstellar medium was more complex, and the boundary between them was more complex than a soap bubble analogy could capture. One of the more startling findings came from Voyager's plasma wave instrument, a sensor designed to detect oscillations in the electrically charged gas surrounding the spacecraft. In the years following the Heliopause crossing, the instrument picked up faint but distinct signals that scientists could use to calculate the density of the plasma Voyager was flying through. The result was surprising. The plasma in the local interstellar medium was denser than expected, but it was also much hotter. Temperatures in the range of 30,000 to 50,000 degrees Celsius. For context, the surface of the Sun sits at about 5,500 degrees. The plasma outside the Heliopause was nearly 10 times hotter. Nobody had predicted that. The models assumed the interstellar medium would be cold, barely above absolute zero. Instead, Voyager was flying through a region of space that was, by any reasonable measure, extremely hot. Hot plasma has more pressure. More pressure means it can push back harder against the solar wind. That could explain part of why the heliosphere was not as large as some models predicted, except the heliosphere was larger, not smaller. The mismatch between expected and observed temperature added another variable to an already complicated problem. The discovery also forced a recalibration of how we think about the Sun's protective role. For years, scientists had talked about the heliosphere as a shield, a bubble that kept dangerous cosmic rays from reaching the inner solar system and irradiating planets like Earth. That picture was not wrong, but it was incomplete. The heliosphere does block some cosmic rays, but the ones it blocks most effectively are the lower energy particles, the ones that would not penetrate Earth's atmosphere or magnetic field anyway. The high-energy cosmic rays, the ones that pose the most risk to astronauts and electronics in space, are much harder to deflect. Many of them punch straight through the Heliopause without slowing down. Voyager's instruments measured cosmic ray intensities on both sides of the boundary and found that while the flux did increase after crossing, the increase was not as dramatic as a simple shield model would predict. The heliosphere is more like a filter than a wall. It reduces the cosmic ray background, but it does not eliminate it. And the fact that the heliosphere is larger than expected does not necessarily mean Earth is better protected. It just means the filtering happens farther out. There is also the question of asymmetry. The solar system is not sitting still in the galaxy. It is moving, barreling through the local interstellar medium at roughly 50,000 miles per hour in the direction of a point in the constellation Hercules. That motion compresses the heliosphere on the leading edge and stretches it out behind like the tail of a comet. Voyager 1 crossed the Heliopause on the nose of the heliosphere, the side facing into the interstellar wind. Voyager 2, which was still inside the heliosphere in 2012, was on a different trajectory. It eventually crossed the Heliopause in November 2018 at a distance of about 119 AU, slightly closer to the Sun than Voyager 1, but in a different direction. The fact that the two spacecraft crossed at different distances confirmed that the heliosphere is not spherical. It is elongated, compressed on one side, stretched on the other. The shape matters because it affects how cosmic rays enter the heliosphere and how the solar wind escapes. Models that assumed a symmetric bubble were missing a huge piece of the structure. By 2020, scientists had stitched together a new picture of the heliosphere based on data from both Voyagers, observations from other spacecraft like IBEX, which mapped the heliosphere's shape from Earth orbit, and updated theoretical models. The new picture was messier. The heliosphere looked less like a teardrop and more like a croissant, with lobes and folds and a turbulent wake trailing behind. The Heliopause itself was not a fixed boundary. It breathed, It expanded and contracted in response to changes in the solar wind driven by the Sun's 11-year activity cycle. During solar maximum, when the Sun was spewing more particles and stronger magnetic fields, the heliopause pushed outward. During solar minimum, it pulled inward. Voyager 1 had crossed during a relatively quiet period. If it had arrived a few years earlier or later, the boundary might have been in a different place. That dynamic behavior meant that any single measurement of the heliopause distance was just a snapshot. The true boundary was a moving target. The implications of Voyager's heliopause discovery extended far beyond our own solar system. If our heliosphere was larger and more complex than models predicted, then the same was probably true for other stars. Every star with a wind, which is essentially every star, carves out its own bubble in the interstellar medium. The size and shape of those bubbles depend on the star's wind strength, the density of the surrounding gas, and the star's motion through space. Understanding our heliosphere in detail gives astronomers a template for thinking about how other stars interact with their neighborhoods. That matters for exoplanet research because a star's heliosphere affects how much cosmic radiation reaches its planets. Planets orbiting stars with weak winds or stars moving through dense interstellar clouds might be bathed in much higher radiation levels than Earth, which could have consequences for habitability. Voyager's data provided the first ground truth measurement of a heliosphere's size and structure. It was a single data point, but in a field where observational data is scarce, a single data point can be worth its weight in gold. The crossing also raised a question that nobody had a good answer for. If the heliopause was this far out, and this dynamic and this poorly understood, what else were we getting wrong? The models that predicted 85 AU were not built by amateurs. They were constructed by some of the best physicists and astrophysicists in the world using equations that had been tested and refined for decades, and yet the models missed by billions of miles. That level of discrepancy suggested that our understanding of plasma physics at these scales, where magnetic fields and charged particles interact over distances larger than the orbits of planets, was incomplete. There were processes happening that the models did not include, mechanisms that mattered but had been left out because nobody knew they were important. Voyager had revealed the gaps. Filling them would take years of work and probably more direct measurements from future missions. One of the engineers at JPL who worked on Voyager in the early days later said that crossing the heliopause felt like watching a car you built in your garage finish a cross-country road trip and then keep driving into the ocean without stopping. The mission was designed for 5 years. 35 years later, it was still delivering surprises. The heliopause was supposed to be the edge of the map, the final landmark before the blank space where there was nothing left to discover. Instead, crossing the heliopause opened up an entirely new category of questions. What was the interstellar medium actually made of at these distances? How did the magnetic field behave beyond the Sun's influence? Were there structures in interstellar space, currents and flows and boundaries that Voyager could detect? The data coming back in 2012 and 2013 suggested the answer to that last question was yes. And the first hint came from something mission scientists started calling the magnetic highway. The heliopause was not the end of the story. It was barely the beginning. Voyager had spent more than 3 decades flying to the edge of the solar system, only to discover that the edge was not a simple line. It was a border region, a no-man's land filled with phenomena that no model had predicted and no theory fully explained. The spacecraft had done what it was built to do. It had gone farther than anyone expected, measured things no one else could measure, and sent back data that forced an entire field of science to reconsider its assumptions. The heliosphere was not a neat bubble. The heliopause was not a clean boundary. The solar system did not end where the textbooks said it would, and somewhere beyond that boundary, in the thin dark space between stars, Voyager 1 was still flying, still transmitting, still finding new things to confuse and amaze the people back on Earth who had built it and sent it on its way nearly half a century earlier. The edge of the solar system had been redefined, and the spacecraft that redefined it was not done yet. The data coming back from Voyager 1 in late 2012 made no sense. That was the polite way the scientists at JPL described it in meetings. The impolite way involved considerably more profanity and significantly less confidence in their own instruments. The spacecraft had crossed the Heliopause in August. That much was clear. The solar wind had dropped by 94% in a single day. The cosmic ray count had spiked. Every indicator pointed to the same conclusion. Voyager was now in interstellar space, outside the protective bubble of the sun's influence, traveling through a region no human-made object had ever measured. The mission was historic. The data were groundbreaking. And then in the months that followed, the instruments started reporting something that by every model, every theory, every reasonable expectation of how magnetic fields should behave at the edge of the solar system should not have been possible. The magnetic field wasn't changing. That was the problem. Or rather, that was the symptom of a much larger problem that took the better part of a year to untangle. Before we get to what Voyager found, you need to understand what everyone expected to find. The sun's magnetic field is not stationary. It rotates with the sun, which completes one full rotation roughly every 27 days. As the sun spins, its magnetic field lines get dragged along, twisting outward into space like the streams of water from a rotating lawn sprinkler. The shape that results is called the Parker spiral, named after the physicist Eugene Parker, who predicted it in the 1950s. By the time the field lines reach the outer solar system, they are wound so tightly that they point almost tangentially, wrapping around the sun in long spirals rather than radiating straight out. The interstellar magnetic field, the field threading through the space between stars, does not belong to the sun. It is generated by the galaxy itself, shaped by the movement of ionized gas through the Milky Way's spiral arms, and influenced by supernova explosions, stellar winds from other stars, and the general churn of plasma on scales spanning hundreds of light years. The direction of the interstellar magnetic field in our neighborhood of the galaxy had been estimated from observations of how starlight gets polarized as it passes through interstellar dust. The estimates suggested the field ran roughly perpendicular to the direction the solar system was moving through space. Think of it like driving a car through a crosswind. The wind hits you from the side, not from the front or the back. The interstellar magnetic field, according to those estimates, should hit the heliosphere from the side. When Voyager crossed the Heliopause, the expectation was that the spacecraft's magnetometer would detect a dramatic shift in the magnetic field direction. One day the field would be pointing in the direction consistent with the Parker spiral, wrapped around the sun. The next day, after crossing the boundary, the field would swing around to align with the interstellar field perpendicular to the sun's influence. That shift would be the smoking gun, the definitive proof that Voyager had left the heliosphere and entered a completely different magnetic environment. The magnetometer data would show a clean rotation, a reorientation of the field lines from solar to interstellar, and the mission scientists could close the book on the Heliopause crossing with confidence. That shift never happened. The magnetometer kept reporting the same field direction it had been measuring for months. The field still pointed in a direction consistent with the sun's Parker spiral. Not perpendicular, not rotated, not aligned with the interstellar field the way every model said it should be. The particle counts had changed, the cosmic rays had flooded in, the solar wind had vanished. By every other measure, Voyager was in interstellar space, but the magnetic field stubbornly refused to acknowledge the crossing. It was as if the spacecraft had walked through a door into a new room, but the furniture had followed it through. The magnetic environment looked the same on both sides of the boundary. That was not supposed to be possible. For months, the team debated what was happening. Some scientists argued that Voyager had not actually crossed the heliopause after all. Maybe the particle count changes were a fluke, a temporary pocket of interstellar material that had leaked through a crack in the boundary. Maybe the spacecraft was still in the heliosheath, that turbulent outer layer of the heliosphere where the solar wind slows down and piles up. The magnetometer data seemed to support that interpretation. If the field was still aligned with the Sun, then the Sun's influence had not ended. Others pointed out that the cosmic ray flux was far too high and the solar wind count far too low for the spacecraft to still be inside. The heliopause was a pressure boundary, not a magnetic boundary. There was no rule that said the magnetic field had to flip at the same location where the particle populations changed. Maybe the two boundaries were offset. Maybe Voyager had crossed the heliopause, but not yet reached the point where the interstellar magnetic field took over. Maybe there was a transition zone where the Sun's field persisted even in interstellar space, threaded through the plasma like a ghost. The debate was not just academic. If the magnetic field direction was the criterion for defining interstellar space, then Voyager was not there yet. If the particle populations were the criterion, then it had arrived. The definition of where the solar system ended depended on which measurement you trusted, and for the first time in the mission's history, the measurements were giving contradictory answers. The situation was frustrating enough that Ed Stone, Voyager's project scientist and the public face of the mission, found himself in the uncomfortable position of announcing at a press conference in September 2013 that Voyager had crossed the heliopause a year earlier, while also admitting that the magnetic field data did not support that conclusion in the way anyone expected. The spacecraft had left the solar system, probably, but the solar system was apparently following it. The explanation for that contradiction came from a discovery that nobody had predicted and that forced a major revision of how scientists thought about the boundary between the heliosphere and interstellar space. In the months leading up to the heliopause crossing, Voyager's instruments had detected something strange. The low-energy charged particle detector, a sensor designed to measure ions and electrons in the spacecraft's immediate vicinity, started recording brief bursts of high-intensity cosmic rays. These were not the usual background cosmic rays that Voyager had been measuring for years. These were sudden spikes, orders of magnitude higher than normal, lasting a few days before dropping back to baseline. The first burst happened in May 2012, 3 months before the official heliopause crossing. The second happened in July, a third in August. Each time, the cosmic ray count would shoot up, hold steady for a while, then fall back down. The pattern repeated irregularly over the course of several months. The team initially assumed the bursts were noise, instrumental glitches caused by the aging electronics or stray radiation hits. But the pattern was too consistent. The spikes were real. Something was letting cosmic rays flood into the spacecraft's vicinity in concentrated pulses. Then one of the scientists noticed something odd. During the bursts, the direction the cosmic rays were coming from was not random. They were not arriving from all directions the way you would expect if the spacecraft were simply flying through a denser patch of interstellar space. They were streaming along the magnetic field lines. Specifically, they were following the field lines outward, away from the Sun. That should not have been possible. Cosmic rays originate outside the solar system. They come from supernova explosions, neutron stars, black holes, events scattered throughout the galaxy. If Voyager were detecting cosmic rays, they should have been arriving from outside, streaming inward as they penetrated the heliosphere. Instead, they were flowing outward as if they had been inside the heliosphere and were now escaping along organized channels. The realization that followed took months to sink in because it violated the basic picture everyone had been working with. The magnetic field at the edge of the heliosphere was not separate from the interstellar magnetic field. It was connected to it. Somewhere in the outer heliosheath, in the region just inside the Heliopause, the Sun's magnetic field lines were running parallel to the interstellar field lines. Not perpendicular, not tangled, parallel. And in places where the two fields aligned closely enough, they were linking up, creating direct magnetic connections between the inside of the heliosphere and the space beyond. Charged particles could flow along those connections the way cars flow along a highway. Cosmic rays from interstellar space could ride the field lines inward, penetrating deep into the heliosheath. Solar wind particles and lower-energy cosmic rays that had been trapped inside the heliosphere could ride the same lines outward, escaping into interstellar space. The bursts Voyager detected were traffic jams, moments when a particularly dense stream of particles funneled along one of these magnetic highways and flooded past the spacecraft. The scientists started calling the structure the magnetic highway. The name stuck because it captured the phenomenon perfectly. This was not a diffuse mixing zone where solar and interstellar particles slowly blended together. It was a coherent, organized structure where particles could travel long distances quickly along well-defined paths. The speed mattered. Normally, cosmic rays trying to penetrate the heliosphere would scatter off magnetic irregularities in the solar wind, bouncing around like pinballs before eventually working their way inward. The process could take years. On the magnetic highway, particles could cover the same distance in days. It was a shortcut, a fast lane bypassing the turbulent mess of the heliosheath and connecting the deep interior of the heliosphere directly to interstellar space. The discovery was published in the journal Science in December 2013, more than a year after Voyager crossed the Heliopause. The paper described the structure, laid out the evidence, and proposed a model for how it formed. The magnetic highway existed because the Sun's magnetic field and the interstellar magnetic field were not as misaligned as earlier estimates had suggested. The interstellar field in the immediate vicinity of the Heliopause ran at an angle that allowed it to come into close contact with the outermost loops of the Sun's Parker spiral. Where the two fields touched, they could reconnect, a process where magnetic field lines from two different sources snap together and rearrange themselves into a new configuration. Magnetic reconnection is common in plasma physics. It happens in the Sun's corona. It happens in Earth's magnetosphere when the solar wind slams into our planet's magnetic field. It happens wherever two magnetic fields with different orientations get pressed together. What was surprising was that it was happening at the Heliopause on a scale large enough to create highways spanning billions of miles. The structure was not uniform. Voyager did not detect one continuous highway. It detected multiple bursts, suggesting the highways came and went, opening and closing as conditions in the heliosheath and the interstellar medium shifted. The solar wind is not constant. It fluctuates with the Sun's 11-year activity cycle and with shorter-term variations driven by solar storms and coronal mass ejections. When the solar wind pressure increased, it could push the Heliopause outward and change the angle at which the Sun's magnetic field met the interstellar field. That changing angle would alter where and when reconnection occurred, opening new highways in some places and closing them in others. The heliosheath was not static. It was breathing, flexing, rearranging itself on timescales of days to months. The magnetic highways were symptoms of that motion, transient features that appeared when the geometry happened to be right. The intensity of the magnetic field inside the highways was another surprise. Voyager's magnetometer measured field strengths roughly 10 times higher than what the spacecraft had been recording in the heliosheath before the highways appeared. 10 times. That was not a small bump. That was a fundamental change in the local environment. Strong magnetic fields meant the plasma was under pressure, compressed by forces acting on it from multiple directions. The compression came from the heliopause itself. The boundary was not a passive dividing line. It was an active interface where the solar wind and the interstellar medium were locked in a constant shoving match. The solar wind pushed outward. The interstellar medium pushed inward. The magnetic field, caught in the middle, got squeezed. The highways formed in regions where the squeezing was particularly intense, where the two sides of the boundary were pressed so tightly together that their magnetic fields had no choice but to merge. One of the more startling implications of the magnetic highway discovery was what it said about particle transport. Scientists had known for decades that the heliosphere acted as a partial shield against galactic cosmic rays. The sun's magnetic field and the turbulent solar wind scattered incoming particles, reducing the cosmic ray flux near Earth by a factor of 2 or 3 compared to what it would be in interstellar space. The magnetic highway complicated that picture. If cosmic rays could bypass the heliosheath entirely by riding along highways, then the shielding effect was weaker than anyone thought. The highways were leaks in the shield. They were not large leaks, at least not compared to the total surface area of the heliosphere, but they were efficient. A small fraction of the heliosphere's surface could account for a large fraction of the cosmic ray flux reaching the inner solar system if the particles funneling through those regions were moving fast enough. The highways changed the equation. They made the heliosphere more porous. The discovery also raised questions about the long-term structure of the heliosheath. If the magnetic field in the outermost layer of the heliosphere was aligning with the interstellar field, then the traditional picture of the heliosheath as a chaotic, turbulent region where the solar wind slowed down and piled up was incomplete. The highways suggested order, organization, a level of structure that the models had not accounted for. The solar wind was not just slowing down randomly, it was being channeled, guided by magnetic fields into specific pathways. Some of those pathways led outward, allowing particles to escape. Others looped back inward, trapping particles in the heliosheath for extended periods before they eventually found a way out. The geometry mattered. The details mattered. And the models that treated the heliosheath as a smooth, featureless layer were missing those details entirely. Ed Stone, in an interview shortly after the science paper was published, described the highways as a fundamentally new kind of structure. He said the team had expected the transition from the heliosphere to interstellar space to be gradual, a slow shift from one environment to another over a distance of several astronomical units. Instead, they found sharp boundaries, abrupt changes, and organized structures that appeared and disappeared on short timescales. The heliosheath was not a transition zone in the sense of a smooth gradient. It was a patchwork, a region where different processes dominated in different places at different times. The highways were one piece of that patchwork. There were probably others that Voyager had not detected yet, or that only existed in parts of the heliosheath the spacecraft would never visit. The debate over whether Voyager had truly left the solar system continued for months after the magnetic highway discovery. Some scientists argued that as long as the spacecraft was still detecting the sun's magnetic field, it had not fully crossed into interstellar space. Others countered that the magnetic field was irrelevant. The heliopause was defined by the particle populations, not the field direction. If the solar wind was gone and the cosmic rays had flooded in, then Voyager was in interstellar space regardless of what the magnetometer said. The argument was partly semantic and partly philosophical. What did it mean to leave the solar system? Was it the point where the sun's gravity stopped mattering? That would put the boundary trillions of miles farther out, well beyond the Heliopause, in a region called the Oort cloud, where icy comets orbited in a vast spherical shell. Was it the point where the solar wind stopped? That was the Heliopause, more or less, though the definition got fuzzy when magnetic highways connected the inside to the outside. Was it the point where the sun's magnetic field stopped? Voyager's data suggested that point might not even exist in the way people assumed. The field did not stop. It transitioned. It merged. It became part of something larger. By 2014, the consensus had shifted. Most scientists accepted that Voyager 1 had crossed the Heliopause in August 2012, even though the magnetic field had not flipped. The highways explained the discrepancy. The spacecraft had entered interstellar space, but it was flying through a region where the sun's magnetic influence persisted because the field lines were physically connected to the interstellar field. Eventually, Voyager would fly far enough that even those connections would fade and the field would finally rotate to align with the purely interstellar direction. But that transition could take years, maybe decades. The spacecraft was in no hurry. It was traveling at 38,000 miles per hour relative to the sun, which sounds fast until you realize it would take 17,000 years at that speed to cover 1 light year. The nearest star, Proxima Centauri, was 4.2 light years away. Voyager would not get there for another 70,000 years, give or take, assuming it did not hit anything along the way. The magnetic highway discovery had practical implications beyond pure science. Understanding how particles move across the Heliopause matters for planning future missions to interstellar space. If cosmic rays can funnel into the heliosphere along organized channels, then spacecraft leaving the solar system need to be designed to handle higher radiation levels than earlier estimates suggested. The highways also matter for understanding space weather. Solar storms can send bursts of high-energy particles outward through the heliosphere. If those particles escape along magnetic highways, they could travel farther and faster than traditional models predict, potentially affecting spacecraft operating in the outer solar system or even beyond. The highways were not just a curiosity, they were a feature of the environment that mission planners and engineers needed to account for. There was also the question of whether other stars had magnetic highways at the edges of their heliospheres. Every star with a wind creates a bubble in the interstellar medium. The size and shape of the bubble depend on the star's wind strength and the local conditions in the surrounding gas. But the basic physics, the interaction between the stellar wind and the interstellar magnetic field, should be the same. If our heliosphere has highways, then other heliospheres probably do too. That has implications for how cosmic rays propagate through the galaxy. If every stellar bubble is leaking particles along highways, then the cosmic ray background in the galaxy is not as uniform as astronomers once thought. There could be lanes, regions where cosmic rays are more concentrated because they are funneling along magnetic structures connecting multiple stellar bubbles. Voyager's discovery at the edge of our own solar system opened a window into understanding how stars interact with their galactic neighborhoods on scales we cannot observe directly. The data kept coming. Even after the Heliopause crossing, even after the magnetic highway discovery, Voyager continued transmitting measurements of the interstellar environment. The plasma wave instrument, which had been mostly quiet during the transit through the heliosheath, started picking up faint oscillations. These were not random noise. They were coherent waves, ripples in the plasma caused by disturbances propagating through the interstellar medium. The waves had a frequency that allowed scientists to calculate the density of the plasma surrounding the spacecraft. The result was a number nobody had expected. The plasma in the local interstellar medium was about 40 times denser than the plasma in the heliosheath just inside the heliopause. 40 times. That density jump was enormous, and it explained part of why the heliopause was so sharp. The boundary was not gradual because the two sides were so different. On one side, you had the hot, tenuous solar wind spreading out from the sun. On the other side, you had the cool, dense interstellar medium pressing inward. The transition between them was abrupt because there was no smooth way to blend such different conditions. The heliopause was a shock front, a discontinuity in the plasma where the properties changed almost instantaneously over a distance much shorter than the spacecraft could resolve. The density measurements also confirmed that the interstellar medium near the Sun was not as empty as astronomers once thought. Space, even the space between stars, is not a perfect vacuum. It is filled with gas, mostly hydrogen, at densities low enough that you would need to collect atoms from a volume the size of a building just to fill a soda can. But low density does not mean the gas is unimportant. The interstellar medium shapes how stars form. It affects how light travels across the galaxy. It determines how cosmic rays scatter and propagate. Voyager's measurements gave scientists their first direct sample of the local interstellar medium's properties, and those properties were feeding into models of how our region of the galaxy evolved over time. The data were the ground truth that every model needed but never had. The magnetic highway was not the last surprise Voyager delivered. It was just the most dramatic example of how little we understood about the edge of the solar system before the spacecraft got there. The models had predicted a smooth, orderly transition from solar to interstellar space. Voyager found chaos, structure, bursts, highways, and a magnetic field that refused to behave the way textbooks said it should. The heliosheath turned out to be one of the most dynamic, complex, and poorly understood regions in the solar system, and Voyager was the only machine that had ever flown through it and lived to send back data. The highways were open, the particles were flowing. The sun's magnetic field was reaching out into interstellar space, connecting the solar system to the galaxy in ways no one had imagined. And somewhere beyond those highways, deeper into the space between stars, Voyager was still flying, still measuring, still finding new things that did not fit the old models. The edge of the solar system was not a line, it was a frontier. And the spacecraft humanity sent to map that frontier had just sent back word that the frontier was stranger than anyone dared predict. Nobody prepared for the sound. That is what keeps coming back in interviews with the scientists and engineers who spent decades working on Voyager. They had planned for every other contingency: instrument failures, communication dropouts, trajectory errors, power loss. They had modeled the heliopause crossing 100 different ways, calculated what the particle counts would do, what the magnetic field should look like, how the cosmic ray flux would spike. They had debated the definition of interstellar space, argued over which measurements mattered most, and prepared press releases announcing the historic moment when humanity's first emissary would leave the solar system and enter the space between stars. What they had not prepared for, what nobody even thought to look for, was a hum, a low-frequency oscillation in the plasma surrounding the spacecraft, faint but persistent, resonating through the charged particles like a note held on an organ pipe. Space was supposed to be silent. Voyager found otherwise. And that hum, more than any particle count or magnetic field reading, more than any boundary crossing or cosmic ray spike, became the clearest proof that the spacecraft had entered an environment fundamentally different from anything it had measured in 35 years of flight. The interstellar medium was not empty, it was not cold, it was not the void astronomers had imagined for a century. It was alive with energy, structured by forces operating on scales we had never directly observed, and it was speaking to us in a language we were only just beginning to decode. The plasma wave instrument was not supposed to be a headline maker. It was one of 10 scientific sensors mounted on Voyager, designed to detect oscillations in the electrically charged gas surrounding the spacecraft. Plasma waves are a common feature of space environments. Earth's magnetosphere is full of them, whistling and crackling as charged particles interact with the planet's magnetic field. The solar wind generates them constantly. Jupiter's magnetosphere, which Voyager flew through in 1979, roared with plasma waves so intense they could be converted into audio and played through speakers, a cacophony of pops and hisses that sounded like a radio tuned between stations. But the instrument had been mostly quiet during Voyager's transit through the outer heliosphere. The plasma in the heliosheath, that turbulent outer layer where the solar wind slows down, was too tenuous and too disordered to generate strong, coherent waves. The instrument recorded data, sure, but the signals were weak, buried under noise, unremarkable. Nobody expected that to change after the Heliopause crossing. The interstellar medium was supposed to be even emptier than the heliosheath. Thinner gas, fewer particles, nothing to generate waves with. The instrument would keep recording, but the data would be background, filler material for papers written by specialists trying to squeeze significance out of marginal signals. Then in October 2012, 2 months after Voyager crossed the Heliopause, the plasma wave instrument detected something. A faint oscillation, steady and coherent, repeating at a frequency just above 2 kHz, 2,000 cycles per second. For context, that is roughly the frequency of the highest note on a standard piano, though calling it a note is misleading. This was not a sound you could hear with human ears. Sound requires air or some other medium to carry vibrations. Space has no air. The oscillation was an electromagnetic wave traveling through plasma, a ripple in the density of charged particles surrounding the spacecraft. But if you converted that oscillation into sound waves at the same frequency and played it through a speaker, it would produce a tone, a hum, low, steady, unvarying. The kind of background noise you stop noticing after a few minutes because your brain filters it out as irrelevant. Except Voyager's instruments did not filter anything out. They recorded everything, and the hum kept showing up in the data week after week, unchanging. At first, the team assumed it was instrumental noise. Voyager was 46 years old by 2012. The electronics had been baked by radiation, frozen in the cold of deep space, and subjected to temperature swings that would have destroyed most consumer devices within months. Glitches were common. The spacecraft had a long history of instruments misbehaving, sending back garbage data that had to be filtered out during analysis. But this signal was too clean to be a glitch. It had structure. It repeated at the same frequency with the same amplitude every time the instrument sampled, and it was correlated with other measurements. When the plasma density changed, the frequency of the oscillation shifted slightly, exactly the way you would expect if the wave were a real physical phenomenon propagating through the surrounding gas. The hum was not coming from inside the spacecraft, it was coming from outside, from the interstellar medium itself. The realization that followed took months to sink in because it contradicted a century of assumptions about what the space between stars was supposed to be like. The interstellar medium, according to models dating back to the early 1900s, was cold, diffuse, and essentially featureless. A near vacuum with densities so low that collisions between atoms were rare events. a place where nothing happened on timescales shorter than millions of years. The only reason astronomers paid attention to it at all was because it affected how light from distant stars traveled to Earth. Interstellar gas absorbed certain wavelengths, leaving dark lines in stellar spectra. Interstellar dust scattered light, making distant objects appear dimmer and redder than they actually were. The medium was an obstacle, a layer of static between us and the rest of the galaxy, not a place where interesting physics occurred. Voyager's plasma wave data suggested that picture was wrong in almost every detail. The hum was a plasma oscillation, a wave mode where electrons in the plasma move back and forth in response to electric fields, creating a traveling disturbance that propagates at a specific frequency determined by the plasma's density. The denser the plasma, the higher the frequency. The relationship is clean, predictable, and had been tested in laboratory plasmas and space environments closer to Earth for decades. The formula was simple enough that undergraduate physics students learnt it in introductory courses. Take the plasma frequency, measure it with an instrument like Voyager's, and you can calculate the electron density directly. No models, no assumptions, just a straightforward conversion from one number to another. When the Voyager team ran the numbers on the hum they were detecting, the result was a density of about 0.002 electrons per cubic centimeter. That might sound like nothing. 0.002 of an electron per cubic centimeter is, by terrestrial standards, an insanely good vacuum. The best laboratory vacuums on Earth struggle to reach densities that low. But the number mattered because it was 40 times higher than what the models predicted for the local interstellar medium near the Heliopause. 40 times, not 10% higher, not double. 40 times denser than the pre-Voyager estimates. The discrepancy was so large that some scientists initially refused to believe it. The models that predicted the lower density were not built by amateurs. They were based on decades of observations, measurements of how radio waves from pulsars got delayed as they traveled through interstellar space, studies of how starlight got absorbed by interstellar gas, and calculations of how much mass was locked up in the hydrogen atoms drifting between stars. The models had been refined and tested and cross-checked. They were supposed to be reliable. And yet Voyager was sitting in the interstellar medium, measuring the plasma directly, and the plasma was 40 times denser than it had any right to be according to those models. Something was wrong. Either the models were wrong, or the region of space Voyager had entered was not representative of the broader interstellar medium. Maybe the spacecraft had crossed the Heliopause into an unusually dense pocket, a local anomaly that happened to be sitting right on the boundary. Maybe the density would drop as Voyager flew farther out. Maybe this was a fluke. It was not a fluke. The density stayed high. Over the following months and years, as Voyager continued transmitting, the plasma wave instrument kept detecting the hum. The frequency shifted slightly as the spacecraft moved, indicating the density was not perfectly uniform, but the average value stayed around 0.002 electrons per cubic centimeter. The interstellar medium near the Heliopause was simply denser than anyone expected. The models had underestimated it by an order of magnitude. And once the team accepted that the measurement was real, the next question was obvious. If the density was 40 times higher than predicted, what else were the models getting wrong? The answer came from the temperature measurements, and those were even more shocking. Temperature in space is a tricky concept because there is no air to carry heat the way there is on Earth. When scientists talk about the temperature of a plasma, they are really talking about how fast the particles are moving. Hot plasma means the electrons and ions are zipping around at high speeds, colliding with each other violently. Cold plasma means the particles are moving slowly, barely interacting. The temperature of the solar wind near Earth sits around 100,000 degrees Celsius, which sounds absurdly hot until you realize that the density is so low you would freeze to death instantly if you stepped outside a spacecraft without a suit. The particles are moving fast, but there are so few of them that they cannot transfer much heat to a solid object. The models predicted the interstellar medium would be cold, just a few thousand degrees above absolute zero, because there was nothing to heat it. No nearby stars, no solar wind, just the faint glow of starlight and the even fainter microwave background left over from the Big Bang. Voyager's measurements told a different story. The plasma temperature in the local interstellar medium was somewhere between 30,000 and 50,000 degrees Celsius, 10 times hotter than the models predicted, hotter than the surface of many stars. The particles in the interstellar medium were not drifting lazily through space. They were racing, slamming into each other with enough energy to ionize atoms and generate the plasma waves Voyager was detecting. The source of all that energy was unclear. There were no obvious heating mechanisms. The sun was too far away to matter. The nearest other stars were light years distant. Supernova explosions, which could heat large regions of the galaxy, were rare, and their effects faded over time. The interstellar medium in our neighborhood of the Milky Way was not supposed to be this hot, and yet it was. Voyager was sitting in it, measuring it, sending the data home, and the data were unambiguous. Space between the stars was not a cold void, it was a furnace. The combination of high density and high temperature had immediate consequences for how scientists thought about the structure of the galaxy. The pressure of a gas, whether it is air in a balloon or plasma in space, depends on both density and temperature. High density and high temperature mean high pressure. The interstellar medium near the Sun was under significantly more pressure than the models predicted. That pressure was pushing inward on the heliosphere, compressing the solar wind bubble from the outside. The heliopause, the boundary where the solar wind and the interstellar medium balance, was not determined solely by the strength of the solar wind. It was determined by the balance between the outward pressure of the solar wind and the inward pressure of the interstellar medium. If the interstellar pressure was higher than expected, the heliopause would be closer to the Sun than models predicted. Except Voyager had found the heliopause farther out than expected, not closer. The only way to reconcile that contradiction was to accept that the solar wind itself was stronger or more persistent at large distances than the models assumed. Both sides of the equation, the solar wind and the interstellar medium, were more complex than anyone had accounted for. The boundary between them was not a simple balance of pressures. It was a dynamic interface shaped by forces operating on multiple scales. The magnetic field measurements added another layer to the picture. The interstellar magnetic field near the heliopause was about 10 times stronger than the solar wind's magnetic field at the termination shock, the inner boundary of the heliosheath, where the solar wind first begins to slow down. 10 times, that was a huge difference. Magnetic fields in plasmas carry energy and exert pressure just like the gas itself. A strong magnetic field can confine plasma, channel it along field lines, and resist compression. The interstellar magnetic field near the heliopause was strong enough to do all of those things. It was not a passive background, it was an active player in shaping the boundary. The field lines ran roughly parallel to the heliopause, wrapping around the heliosphere like bands around a barrel. When the solar wind tried to push outward, it had to push against both the interstellar gas and the interstellar magnetic field. The combined resistance was greater than the sum of the parts because the field and the gas were coupled. Compress the gas and you compress the field. The field pushes back. The result was a boundary that was stiffer, more resistant to changes than a simple gas versus gas interface would be. One of the scientists who worked on analyzing Voyager's interstellar data, Don Gurnett at the University of Iowa, later described the plasma hum as one of the most surprising discoveries of the entire mission. He pointed out that the hum was not just a curiosity, it was a tool. Every time the plasma wave instrument detected the oscillation, it was taking a direct measurement of the electron density in the spacecraft's immediate vicinity. No models, no assumptions about what the interstellar medium should be like based on observations of distant stars, just a straightforward measurement of how many electrons were sitting in a cubic centimeter of space around Voyager. That kind of ground truth data was almost impossible to get any other way. Astronomers had been studying the interstellar medium for a century using indirect methods, watching how it affected light and radio waves passing through it. Voyager was the first spacecraft to actually sit in the interstellar medium and sample it directly. The hum was proof that the sampling was working, and the results were forcing a complete rethink of what the space between stars was actually like. The density and temperature measurements fed into broader questions about the structure of the galaxy. The Milky Way is not uniform. It has spiral arms dense with stars and gas, and it has voids where the density drops to almost nothing. The Sun sits in a relatively empty region called the local bubble, a cavity roughly 300 light-years across that was carved out by supernova explosions millions of years ago. The explosions heated and dispersed the gas, leaving behind a low-density bubble filled with hot, tenuous plasma. The models predicted that the interstellar medium inside the local bubble would be cold and diffuse because the supernova energy had long since dissipated. Voyager's measurements suggested that was not quite right. The plasma was hot, hotter than it should be if the only heating source was ancient supernova remnants. Something else was keeping the temperature up. One possibility was that the Sun itself was contributing. The solar wind, even though it weakens with distance, still carries energy outward. That energy has to go somewhere. When the solar wind slams into the heliopause, it heats the surrounding plasma. Over billions of years, the cumulative effect of countless stars like the Sun blowing winds into the local bubble could maintain a higher temperature than supernova heating alone would produce. Voyager's data supported that idea, though proving it would require measurements from other parts of the local bubble that no spacecraft had visited. The plasma hum also revealed something unexpected about how disturbances propagate through the interstellar medium. In 2013, a year after Voyager crossed the heliopause, the plasma wave instrument detected a sudden spike in the hum's intensity. The frequency jumped, indicating the density had increased sharply. The spike lasted several weeks before fading back to baseline. The team traced the event back to a solar storm that had erupted months earlier and sent a shockwave rippling outward through the heliosphere. When the shockwave reached the heliopause, it compressed the interstellar plasma on the other side, creating a temporary density increase that Voyager detected as a frequency spike. The fact that a disturbance originating at the Sun could affect the plasma density in interstellar space was remarkable. It meant the heliopause was not a perfect barrier. It was permeable. Energy and particles could cross it, carried by shock waves and magnetic disturbances. The interstellar medium and the heliosphere were not isolated from each other. They were coupled, constantly exchanging energy and mass across the boundary. The discovery had implications for understanding space weather throughout the galaxy. Every star with a wind creates a heliosphere. Every heliosphere interacts with the surrounding interstellar medium. If disturbances from one star's wind can propagate across the heliopause and affect the plasma outside, then the interstellar medium is constantly being stirred by the collective influence of billions of stars. The galaxy is not a static collection of isolated bubbles. It is a dynamic, interconnected web where disturbances in one region can propagate across light years and influence conditions in another. Voyager's measurements of the plasma hum were the first direct evidence of that coupling. The interstellar medium was not a passive backdrop. It was an active participant in the galaxy's evolution, shaped by the stars embedded within it and shaping those stars in return. The temperature and density measurements also changed how scientists thought about the formation of new stars. Stars form when dense clouds of gas collapse under their own gravity. The denser the gas, the easier it is for gravity to pull it together. The hotter the gas, the harder it is for gravity to win because the thermal pressure pushes outward, resisting collapse. The interstellar medium near the Sun was hotter and denser than models predicted, which meant the balance between gravity and pressure was different than astronomers had assumed. In regions like the local bubble, where the gas was hot, star formation should be suppressed. The thermal energy would prevent clouds from collapsing, but the higher density partially offset that effect. More particles meant more gravity. The net result was a star formation rate that depended sensitively on the local conditions, varying from place to place across the galaxy in ways that large-scale models could not capture. Voyager's data provided a single data point, a measurement of the interstellar medium in one specific location at one specific time. But that data point was the only direct measurement anyone had. It was the ground truth that every model of the galaxy needed but had been missing for a century. By 2014, the Voyager team had published a series of papers in the journal Science, detailing the plasma wave measurements and what they revealed about the interstellar medium. The papers were dense, filled with equations and graphs that only specialists could fully pass, but the conclusions were clear enough that they made headlines. The space between stars was not empty, it was not cold, it was not the featureless void textbooks had described for decades. It was a complex, dynamic, energetic environment shaped by magnetic fields, stellar winds, and the leftover energy from ancient supernova explosions. The interstellar medium mattered, not just as an obstacle between us and distant stars, but as a fundamental component of the galaxy's structure and evolution. Voyager had given us our first real look at that environment, and the view was nothing like what anyone expected. Ed Stone, in a press conference announcing the plasma wave findings, said something that stuck with the journalists who covered the story. He said the interstellar medium was speaking to us, and Voyager was listening. The hum was not random noise, it was information. Every oscillation carried data about the density, temperature, and magnetic field of the plasma. Every spike and dip in frequency told a story about disturbances propagating through space, shock waves from the sun, or density fluctuations caused by processes we did not yet understand. The spacecraft was not just passively recording data. It was actively sampling a living, breathing environment that had never been studied this way before. And the more we listened, the more we realized how little we actually knew about the galaxy we lived in. The plasma hum was still there as of the last data transmission in early 2025. 47 years after launch, Voyager was still detecting the oscillation, still measuring the density of the interstellar medium, still sending back data at a rate of 160 bits per second across 15 billion miles of empty space. The hum had become a constant companion, a background tone that mission scientists checked every time new data arrived. It was proof that the spacecraft was still functional, still flying, still exploring a region of space no human would ever visit in person. The interstellar medium had welcomed Voyager with a sound, a low, steady hum that resonated through the plasma like a voice saying, "You are here. You have crossed the boundary. This is what lies beyond." And Voyager, obedient machine that it was, recorded the hum and sent it home. A message from the void. The first whisper from interstellar space. The implications of Voyager's interstellar measurements extended far beyond our own solar system. If the local interstellar medium was this different from what models predicted, then the same was probably true for other regions of the galaxy. Every measurement Voyager made, every density spike, every temperature reading, every magnetic field twist, fed into a broader understanding of how galaxies work. The Milky Way is a spiral galaxy, a flat disk of stars and gas, rotating around a central bulge. The stars orbit the center, but they are not alone. They drag their heliospheres with them, carving bubbles in the interstellar medium as they move. Those bubbles interact, overlap, merge. The collective effect of billions of stars blowing winds shapes the large-scale structure of the galaxy in ways that astronomers are only beginning to model. Voyager's data provided the first direct constraint on those models. A single point in a vast galaxy, yes, but a point measured with unprecedented precision, a benchmark that every future model would have to match. The spacecraft had done what it was built to do. It had flown farther than any human-made object, crossed boundaries no one had ever measured directly, and sent back data that rewrote textbooks. The interstellar medium was no longer a theoretical construct inferred from distant observations. It was a place Voyager had visited, a place we now knew, in concrete detail, to be hotter, denser, and more dynamic than a century of astronomy had predicted. The void between stars was not empty. It hummed, it pulsed, it carried energy and information across distances that defied human comprehension. And somewhere in that hum, in the faint oscillations of plasma rippling around a 47-year-old spacecraft, was a message that would take decades to fully decode. The interstellar medium was not silent. It had been speaking all along. We just needed to send a machine far enough to hear it. Voyager heard it. And now, billions of miles from home, with power fading and instruments shutting down one by one, the spacecraft was still listening, still recording, still transmitting the whispers from the void back to the world that built it and sent it on its way. The interstellar medium had more to say, and as long as Voyager's transmitter kept working, we would keep listening. Because beyond the Heliopause, beyond the reach of the solar wind, in the space where stars end and the galaxy begins, there were disturbances moving, shock waves and storms and ripples in the plasma that no one had expected to find, and Voyager was about to fly straight through them. The hum was not the only thing speaking to Voyager from the depths of interstellar space. There was something else out there, something louder, more violent, and infinitely more surprising, a disturbance that had no business existing where Voyager was flying. A shockwave, a wall of compressed plasma traveling at 4.5 million miles per hour, slamming through the interstellar medium like a freight train with no brakes. And the truly bizarre part, the detail that made scientists at JPL stare at their screens in disbelief when the data first came in, was that this shockwave had started its journey at the Sun, 93 million miles from Earth. 12 billion miles from where Voyager was sitting. The Sun had thrown a punch so hard it reached across the entire solar system, crossed the Heliopause and kept going. A solar tsunami propagating through interstellar space. Nobody predicted that. Nobody thought it was possible. And yet Voyager's instruments were recording it in real time, measuring the waves as they rolled past the spacecraft like ripples on a pond. Except the pond was the size of the solar system, and the ripples were traveling faster than anything humanity had ever built. The discovery came from data recorded in April 2012. 4 months before Voyager officially crossed the Heliopause. The spacecraft was still in the heliosheath at the time, that chaotic outer layer where the solar wind slows down and piles up against the pressure of the interstellar medium. The plasma wave instrument, the same sensor that would later detect the interstellar hum, picked up a sudden spike in oscillations. The frequency jumped. The amplitude increased by an order of magnitude. The signal looked like a wave, a coherent pulse moving through the plasma with a well-defined shape and a clear direction of propagation. It lasted several days, then faded back to baseline. The team recorded the event, flagged it as unusual, and moved on. There were 100 other things to worry about in April 2012. Voyager was approaching the heliopause. The instruments were behaving erratically. The power budget was getting tighter every year. A single unexplained wave in the plasma data was not a priority. Then it happened again. In October 2012, 2 months after the heliopause crossing, the plasma wave instrument detected another spike. Same shape, same frequency jump, same pattern of a sharp rise followed by a gradual decay. This one was stronger than the first, lasting longer and carrying more energy. The scientists at JPL started paying attention. 2 events with the same signature, separated by 6 months, both occurring during periods when Voyager was flying through a transition zone between the heliosphere and the interstellar medium. That was not a coincidence. That was a pattern. And patterns in space data usually mean something real is happening, something that can be traced back to a physical process with a cause and an effect. The third wave arrived in April 2013. By this point, Voyager was firmly in interstellar space, more than 1 billion miles beyond the heliopause, flying through plasma that by every definition belonged to the galaxy and not to the sun. The solar wind was gone. The magnetic field had transitioned. The cosmic ray count was high. Voyager was outside. And yet the plasma wave instrument detected the same spike, the same oscillation, the same unmistakable signature of a disturbance moving through the charged gas surrounding the spacecraft. 3 waves, 3 separate events, each one separated by roughly 6 months. The timing was too regular to be random. Something was generating these waves on a schedule, and that something had to be powerful enough to send shockwaves across 12 billion miles of space. The answer, when the team finally pieced it together, came from the sun, specifically from solar storms. The sun is not a calm star. Its surface roils with magnetic activity, twisting and kinking the field lines until they snap and release enormous bursts of energy. Sometimes that energy emerges as a solar flare, a sudden brightening of the sun's surface that floods the solar system with X-rays and ultraviolet light. Other times, the energy launches a chunk of the sun's outer atmosphere into space. Astronomers call these events coronal mass ejections, or CMEs. A typical CME carries billions of tons of plasma, electrons and protons, and heavier ions, hurled outward at speeds that can exceed 2 million miles per hour. When a CME reaches Earth, it slams into our planet's magnetic field, compressing it, triggering auroras, and occasionally disrupting satellites and power grids. CMEs are one of the primary drivers of space weather, the term scientists use to describe the constantly shifting environment of particles and fields that fills the solar system. The Sun launched a major CME in March 2012, another in August 2012, a third in March 2013. Each eruption sent a shockwave rippling outward through the solar wind, compressing the plasma ahead of it the way a boat's bow compresses water. The shockwaves traveled fast, much faster than the solar wind itself, because they were riding on top of the wind, surging ahead like a tidal wave driven by an underwater earthquake. By the time the shockwaves reached the outer heliosphere, they had been traveling for months, covering billions of miles. The solar wind at those distances was already slow, barely supersonic, and the shockwaves compressed it even further as they passed. When the shockwaves hit the heliopause, the boundary between the heliosphere and the interstellar medium, something extraordinary happened. They did not stop. They punched through. The heliopause is a pressure boundary, not a wall. It exists because the outward push of the solar wind balances the inward push of the interstellar medium. But that balance is not rigid. It flexes. Push hard enough from one side and the boundary moves. A shockwave from a CME carries an enormous amount of momentum. When it hits the heliopause, it compresses the boundary, squeezes it inward, and some of that energy leaks across into the interstellar medium on the other side. The leakage is not a gentle transfer. It is a pulse, a sudden compression of the interstellar plasma that propagates outward as a wave, carrying the memory of the original solar storm with it. The wave travels at the speed of sound in the interstellar medium, which turns out to be around 2,000 kilometers per second, 4.5 million miles per hour, fast by any standard, though still much slower than the speed of light. The waves Voyager detected in 2012 and 2013 were the echoes of those CMEs, solar tsunamis, shockwaves that had traveled from the Sun through the heliosphere, across the heliopause, and into interstellar space, covering a distance equivalent to twice the diameter of the solar system before finally reaching the spacecraft. The travel time from the Sun to Voyager was roughly 6 months, which matched the spacing between the waves. The Sun launched a CME. 6 months later, Voyager detected a plasma wave. The correlation was perfect. The waves were not random noise, they were signals, disturbances propagating through space at predictable speeds, carrying information about the solar storms that had created them. The discovery was published in the journal Nature in 2014 by a team led by Farah al-Sheikh, a researcher at the University of Michigan who had spent years analyzing Voyager's plasma wave data. The paper was titled "Solar Tsunamis at the Edge of the Heliosphere," and it caused a stir in the space physics community because nobody had expected CMEs to affect the interstellar medium this way. The heliosphere was supposed to shield the galaxy from the Sun's activity. The heliopause was supposed to absorb shockwaves, not transmit them. The fact that energy from solar storms could propagate 12 billion miles into interstellar space meant the Sun's influence extended far beyond the bubble most scientists had drawn around it. The heliosphere was not a sealed container. It was porous, it leaked, and the leaks carried energy across a boundary that was supposed to be a wall. The implications were immediate and far-reaching. The first and most obvious was that the heliopause was dynamic in ways the models had not accounted for. It did not just sit there passively separating the solar wind from the interstellar medium. It moved, it breathed. Every time a CME hit the heliopause, the boundary compressed inward, then rebounded outward as the pressure wave passed. The motion was small, a few astronomical units at most, but it was real. Voyager had not crossed a static line in space. It had crossed a rippling, flexing interface that responded to every major disturbance in the solar wind. The spacecraft had flown through the heliopause in August 2012 during a relatively quiet period. If it had crossed a few months earlier or later, during the peak of a CME impact, the boundary might have been in a completely different location. The heliopause was not a fixed address, it was a moving target. The second implication was more subtle, but equally important. The waves provided a tool for measuring the density of the interstellar medium. When a wave propagates through plasma, its speed depends on the plasma's properties. Denser plasma slows the wave down, hotter plasma speeds it up. By measuring how fast the waves traveled and how much they compressed the plasma as they passed, scientists could calculate the density and temperature of the interstellar medium along Voyager's trajectory. The technique was similar to how seismologists use earthquake waves to map the interior of the Earth. The waves were probes, natural experiments that revealed the structure of the environment they traveled through. Every tsunami Voyager detected was a measurement, a data point that could be plugged into models of the interstellar medium and used to refine our understanding of what the space between stars actually looked like. The density measurements that came from the tsunami waves resolved a long-standing puzzle. Before Voyager, astronomers had estimated the density of the interstellar medium near the Sun using indirect methods. They looked at how radio waves from pulsars got delayed as they traveled through space. They measured how much starlight got absorbed by interstellar gas. They counted the number of hydrogen atoms along lines of sight to distant stars. All of those methods pointed to a density of around 0.0005 electrons per cubic centimeter. That was the number in the textbooks, the value that went into models of the heliosphere. But the tsunami waves told a different story. When Al-Sheikh and her team analyzed the speed and compression of the waves, they calculated a density of about 0.002 electrons per cubic centimeter, 4 times higher than the textbook value, not double, not 50% higher, 4 times. The discrepancy was enormous, and it meant that every model of the heliosphere built before Voyager had underestimated the pressure pushing inward from the interstellar medium. The higher density explained several mysteries that had been nagging at scientists for years. It explained why the Heliopause was closer to the Sun than some models predicted. Higher interstellar pressure meant the solar wind got compressed into a smaller bubble. It explained why the cosmic ray flux near Earth was lower than calculations suggested it should be. A denser interstellar medium provided more shielding, scattering cosmic rays before they could reach the inner solar system. It explained why the heliosphere's shape was more asymmetric than simple models allowed. Higher pressure on one side of the Heliopause, the side facing the direction the Sun was moving through the galaxy, would compress the heliosphere into a teardrop shape rather than a sphere. The tsunami waves had given scientists a direct measurement of a quantity that had been guessed at for decades. And the measurement revealed that the guesses had been wrong by a factor of 4. Don Gurnett, the principal investigator for Voyager's plasma wave instrument, described the tsunami discovery as one of the most unexpected findings of the entire mission. He pointed out that the plasma wave instrument was the only sensor on board Voyager that could detect the waves because they were traveling through a medium that was too tenuous to affect most other instruments. The magnetometer could not see them. The particle detectors could not measure them directly. The plasma wave instrument, which had been designed in the 1970s to study Jupiter's magnetosphere, turned out to be the perfect tool for measuring disturbances in the interstellar medium 40 years later. It was like building a telescope to look at the moon, and discovering it also worked for observing galaxies. The instrument was doing something its designers had never imagined it would need to do, and it was doing it flawlessly. The waves also provided the first direct evidence of how solar storms interact with the interstellar medium. Before Voyager, scientists knew that CMEs could affect the heliosphere. They knew the shock waves compressed the solar wind and accelerated particles to high energies. But they did not know whether those effects stopped at the Heliopause or whether they propagated beyond it. The tsunami waves proved that the effects did not stop. They continued. The Sun's activity was not confined to the heliosphere. It echoed into interstellar space, sending pulses of energy across distances that dwarfed the orbits of the planets. Every major solar storm left a ripple in the interstellar medium, a faint but measurable signature that propagated outward for years after the original eruption. The Sun was not a quiet neighbor. It was loud, broadcasting its presence into the galaxy with every CME it launched. The scale of the waves was staggering. The shockwave from the March 2012 CME traveled outward at 2,000 kilometers per second. It took 6 months to reach Voyager at a distance of 17 billion kilometers from the Sun. By the time it arrived, the wave had spread out over a surface area roughly the size of the heliosphere itself. The energy in the wave was diluted, spread thin across billions of square kilometers, but the total energy was still enormous. Estimates suggested the wave carried roughly 10 to the 32nd power joules of energy, equivalent to 1 billion nuclear bombs. That energy was not concentrated in one place. It was distributed across the entire heliosphere, a faint push that compressed the interstellar plasma by a few percent as it passed. Voyager detected the compression as a spike in the plasma oscillation frequency. The spike lasted several days, then faded as the wave moved on, traveling deeper into interstellar space where no instrument would ever measure it again. The discovery raised questions about how common these waves were. Voyager had detected 3 clear events between 2012 and 2013, all of them linked to major CMEs, but the Sun launches dozens of CMEs every year during periods of high activity. Not all of them are strong enough to generate waves that propagate across the heliopause, but some are. The team estimated that the interstellar medium near the heliopause was probably being hit by solar tsunami waves several times per year during solar maximum, the peak of the Sun's 11-year activity cycle. During solar minimum, when the Sun was quiet, the waves would be rarer, but they never stopped completely. The Sun was always active to some degree, always throwing off CMEs, always sending shockwaves rippling through the heliosphere. Voyager had caught 3 of them. How many others had passed by unnoticed before the spacecraft arrived? How many more would roll past in the years to come? The waves also had implications for understanding space weather throughout the solar system. When a CME launches from the Sun, it takes a few days to reach Earth. By the time it gets to Jupiter, roughly 5 times farther out, it has weakened but is still capable of affecting the planet's magnetosphere. Beyond Jupiter, in the outer solar system, the effects of individual CMEs had been considered negligible. The solar wind was too slow, the distances too great. But the tsunami waves showed that CME shock waves could propagate all the way to the heliopause and beyond, maintaining their coherence over distances of more than 100 astronomical units. That meant spacecraft operating in the outer solar system, missions to the Kuiper Belt or future probes heading toward interstellar space would need to account for space weather effects far beyond what current models predicted. The Sun's reach was longer than anyone thought. There was also a protective effect that nobody had anticipated. The tsunami waves, as they propagated outward, compressed the interstellar medium. That compression created a temporary barrier, a region of higher density plasma that cosmic rays had to penetrate before reaching the inner solar system. The effect was small, a few % reduction in cosmic ray flux at most, but it was real. Every major solar storm effectively thickened the shield around the solar system for a brief period, pushing back against the flood of galactic cosmic rays trying to penetrate the heliosphere. The Sun was not just a source of radiation, it was also, paradoxically, a shield, using its own eruptions to create temporary defenses against radiation from the galaxy. The balance between the two effects, the harmful particles from CMEs and the protective compression of the interstellar medium, was complex and depended on the timing and strength of the storms. Ed Stone, in a press conference announcing the tsunami findings, said the discovery had changed how scientists thought about the boundary of the solar system. He said the heliopause was not a wall, it was a membrane. Thin, flexible, permeable. Energy and particles could cross it in both directions. The solar wind leaked out, cosmic rays leaked in, and disturbances from solar storms sent waves propagating through the interstellar medium like ripples on a pond. The membrane was constantly in motion, responding to every push and pull from both sides. Voyager had spent years crossing that membrane, measuring it layer by layer, and the data were revealing a picture of the heliopause that was far more dynamic and interconnected than the clean boundary drawn in textbooks. One of the more surprising aspects of the tsunami waves was how well defined they were. Space is usually chaotic. Plasma in the heliosphere and the interstellar medium is full of turbulence, random fluctuations in density and magnetic field that scatter waves and break up coherent structures. The fact that the tsunami waves maintained their shape over 12 billion miles of travel suggested that the interstellar medium near the heliopause was calmer than expected. The turbulence was there, certainly, but it was weak enough that large-scale waves could propagate without being torn apart. That calmness was itself a discovery. It meant the local interstellar medium was not a storm-tossed sea. It was more like a lake, gently rippling under the influence of disturbances from nearby stars, but not violent enough to erase the signals those disturbances carried. The waves also provided a way to study the large-scale structure of the heliosphere. When a tsunami wave hit the heliopause, it did not hit uniformly. The heliopause was not a perfect sphere. It was elongated, compressed on the side facing the direction the sun was moving, and stretched out behind. The wave hit the nose of the heliosphere first, then spread around the sides, taking longer to reach the tail. By measuring the timing and shape of the waves at Voyager's location, scientists could infer the three-dimensional shape of the heliopause and how it responded to the pressure pulse. It was like using sonar to map the shape of an underwater object. The waves bounced off the heliopause, and the echoes carried information about the boundary's geometry. Voyager was not just flying through the heliosphere, it was mapping it, using the sun's own eruptions as a probe. The long-term monitoring of the tsunami waves revealed another unexpected detail. The waves did not always arrive when predicted. The March 2012 CME launched from the Sun in late March, and the corresponding wave reached Voyager in September, 6 months later. But the timing was not exact. The wave arrived a few days earlier than models predicted, suggesting the interstellar medium between the Sun and Voyager was slightly less dense than the average density calculated from earlier measurements. The October 2012 wave arrived a few days late, suggesting the density had increased. The variations were small, a few percent at most, but they were real. The interstellar medium was not uniform. It had structure, regions of higher and lower density, and those regions shifted over time. The tsunami waves were revealing that structure, providing snapshots of the interstellar medium's density profile as Voyager flew through it. By 2015, the Voyager team had detected at least 5 distinct tsunami waves, each one linked to a major CME from the Sun. The waves were becoming a regular feature of the data, expected rather than surprising. Scientists started using them as a diagnostic tool, a way to monitor the state of the interstellar medium in real time. Every time a major CME launched from the Sun, the team could predict when the corresponding wave would reach Voyager and what it should look like. When the wave arrived, they compared the prediction to the measurement. The differences told them how the interstellar medium had changed in the months since the last wave. It was a slow process, limited by the fact that waves only arrived a few times per year, but it was the only way to study the interstellar medium at this level of detail. No other spacecraft was out there. No other instrument could make these measurements. Voyager was alone, and the tsunami waves were its window into the structure of the galaxy. The discovery also highlighted just how far the Sun's influence extended. The heliopause was not the edge of the sun's domain. It was just the edge of the region where the solar wind was faster than the speed of sound. Beyond the heliopause, the sun's magnetic field persisted, threaded through the interstellar medium along the magnetic highways Voyager had discovered. And beyond even that, the sun's energy continued to propagate, carried by tsunami waves that rippled through the interstellar medium for years after the original eruption. The sun's reach was measured not in astronomical units but in light months. The sphere of influence was vast, stretching across distances that spacecraft traveling at 38,000 miles per hour would take decades to cross. The solar system was not a small corner of the galaxy. It was a bubble of activity, a region where one star's output dominated the environment for trillions of miles in every direction. The tsunami waves were still being detected as of Voyager's last clear transmission. 47 years after launch, the spacecraft was more than 15 billion miles from the Sun, flying deeper into interstellar space every second, and the plasma wave instrument was still recording the echoes of solar storms launched years earlier. Each wave was a reminder that the Sun had not let go. Its energy was still reaching out, still touching Voyager, still shaping the environment the spacecraft was flying through. The heliopause was behind Voyager, billions of miles in the past, but the Sun's presence was not. It traveled with the spacecraft, carried on magnetic field lines and plasma waves, a faint but undeniable signature that would take years, maybe decades, to finally fade. The solar system did not end with a clean line. It ended with a whisper, a gradual dimming of the sun's influence as distance and the interstellar medium finally absorbed the energy that had been racing outward since the beginning of the solar system. The tsunami discovery was not the last surprise Voyager had in store. There were more mysteries waiting in the data, more questions that would take years to answer. But the waves had proven something fundamental. The edge of the solar system was not a quiet place. It was not a static boundary where nothing happened and nothing changed. It was an active, dynamic, constantly shifting interface where the sun's energy collided with the galaxy, and the result was chaos, order, and a level of structure that nobody had predicted. Voyager had flown into that interface, measured it, mapped it, and sent the data home. And somewhere in those measurements, in the timing of the waves and the shape of the plasma oscillations, was a story that would take decades to fully understand. The Sun had launched a storm. The storm had crossed the solar system, punched through the heliopause, and propagated into interstellar space. Voyager had caught it on the other side, recorded its passage, and sent the message back to Earth. A solar tsunami, traveling across the stars, carrying with it the proof that the sun's voice reached farther than anyone ever imagined. The spacecraft had crossed the boundary, but the boundary had not ended, it had just moved. And Voyager, faithful machine that it was, kept flying, kept measuring, kept sending back the echoes of a star that refused to be silent even in the depths of interstellar space. The tsunami waves were still out there, rolling onward into the dark, carrying their cargo of solar energy toward regions no human would ever see. And somewhere on those waves, encoded in their shape and timing, was a message that humanity had sent without knowing it. A declaration that this star, this small yellow sun in an unremarkable corner of the galaxy, was here, was active, and would not be ignored. The waves carried that message outward, and they would keep carrying it long after Voyager's transmitter finally fell silent and the spacecraft became just another piece of debris drifting through the dark. But that silence had not arrived yet. Voyager was still talking, still transmitting. And aboard the spacecraft, mounted on a side panel where it had sat untouched for 47 years, was a 12-inch gold-plated copper disc carrying sounds and images from Earth, the Golden Record. A message deliberately sent, carefully crafted, intended for an audience that might never exist. And as Voyager flew deeper into interstellar space, that record was finally reaching the place it had been designed for. The void between stars. The place where humanity's message could travel forever, untouched, waiting for someone, someday, to find it and listen. Nobody planned to send a love letter to the universe. That was not on the mission checklist. Voyager was designed to fly past Jupiter and Saturn, take pictures, measure magnetic fields, and then coast into oblivion. 5 years, maybe a decade if the engineers got lucky. The spacecraft would die eventually, power fading, instruments shutting down one by one, and whatever was left would drift through the outer solar system as a piece of frozen junk until the sun burnt out or a collision with something ended the journey. That was the plan. A scientific mission with a defined lifespan and a clear endpoint. Except Carl Sagan had a different idea. He thought Voyager should carry something with it. Not more instruments, not backup systems or extra fuel, a message. A deliberate, carefully constructed artifact that said to anyone or anything that might someday find the spacecraft drifting through the void between stars, "We were here, this is what we were, and this is what we cared about." The idea was absurd by every practical measure. The odds of an alien civilization stumbling across a refrigerator-sized probe in the vastness of interstellar space were so close to zero that calling them astronomical would be an insult to astronomy. But Sagan did not care about the odds, he cared about the gesture. And in the summer of 1977, 6 weeks before Voyager 1 launched, NASA gave him permission to try. The concept was simple, in the way that climbing Everest is simple. You put one foot in front of the other until you reach the top. Sagan and his team had 6 weeks to compile a record, an actual phonograph record like the ones people played on turntables in their living rooms, that would contain sounds and images and music representing the entire breadth of human civilization. Not American civilization, not Western civilization, human civilization. Every culture, every language, every type of music and art and science humanity had ever produced. Compress all of that into 90 minutes of audio and 116 pictures encoded into analog grooves on a 12-inch copper disc. Design a cover that would explain to an alien intelligence how to play the record without assuming they had hands or eyes or any concept of what a phonograph was, and do it all in less than 2 months because the launch window was not going to wait. The team that assembled to make this happen was small, underfunded, and completely overwhelmed, and they pulled it off. Sagan was the driving force, but he was not alone. His partner in the project, in work and in life, was Androyan, a writer and producer who had been collaborating with Sagan on a book about the search for extraterrestrial intelligence. Druyan took on the task of selecting the music, a job that sounds straightforward until you realize you are trying to represent every musical tradition on Earth using a format that can hold 90 minutes of audio, and the result will be judged, if it is ever judged at all, by beings whose concept of music might be completely alien to anything humans have ever created. How do you choose? Do you go with Mozart because his compositions are mathematically elegant? Do you include rock and roll because it represents a specific moment in human culture? Do you add folk music from cultures that have been making music longer than Europe has had written language? Every choice was a compromise. Every selection meant leaving out 1,000 others. The team started with Bach. Johann Sebastian Bach, the 18th century German composer whose work was considered by many musicologists to be the pinnacle of Western classical music. They included 3 separate Bach pieces on the record: the Prelude and Fugue in C major from the Well-Tempered Clavier, The Gavotte en Rondeau from the Partita in E major for solo violin. The Brandenburg Concerto No. 2, that much was non-negotiable. Sagan and Dryan both believed that if there was one composer whose work could communicate the depth and complexity of human thought through sound, it was Bach. There is a story, probably apocryphal but repeated often enough, that it has become part of the Voyager mythology, about a conversation Sagan had with a colleague who asked why they were including so much Bach. Sagan supposedly replied, "Because it would be boasting." The story is almost certainly made up, but it captures the attitude the team brought to the project. They were not just sending music, they were sending proof that humanity could create beauty. Beyond Bach, the selections got more eclectic. Beethoven's Fifth Symphony, Stravinsky's Rite of Spring, a Navajo night chant, a Pygmy girl's initiation song from Zaire, Indian classical music performed on the sitar, a Japanese shakuhachi piece, Chuck Berry's Johnny B. Good, which caused a minor controversy because some members of the team thought rock and roll was too frivolous to represent humanity to an alien civilization. Dryan fought to keep it. She argued that the song captured something essential about human creativity and joy, and if aliens were going to judge us, they should judge us honestly, not as some sanitized version of ourselves that only included the high culture we thought made us look sophisticated. Chuck Berry stayed on the record. The sounds were even harder to compile than the music. The team wanted to include noises that represented life on Earth in a way that did not require language: the sound of wind, the sound of rain, thunder, waves crashing on a beach, a fire crackling, birds singing, dogs barking, footsteps, a heartbeat, a kiss, the sound of a mother and child, a blacksmith hammering metal, a train, a horse and cart, a tractor, a bus, a rocket launching. The final list included 116 separate sounds, each one selected because it represented something fundamental about human experience or the environment we lived in. Some of the sounds were obvious: the cry of a baby, the laughter of children. Others were more abstract: the sound of a pulsar, a rapidly spinning neutron star emitting radio waves at precise intervals, was included because it represented humanity's ability to detect and measure phenomena beyond our own planet. The team was not just documenting Earth, they were documenting what humans had learned about the universe. The images were the most technically challenging part of the project. Phonograph records do not store images naturally. Audio is a one-dimensional signal, a series of vibrations over time. Images are two-dimensional, requiring a completely different encoding scheme. The solution was to convert each image into a series of audio tones, essentially turning the pictures into sound. Each horizontal line of an image was translated into a waveform, and those waveforms were etched into the record in sequence. An alien civilization playing the record would hear what sounded like static or noise, but if they understood the encoding scheme and converted the audio back into a visual format, they would see the images. That was a big if. The team included diagrams on the record's cover explaining how to decode the images, but those diagrams assumed the aliens had some understanding of mathematics, physics, and the concept of representing three-dimensional objects in two dimensions. It was a gamble, a necessary gamble, because without the images, half the message would be lost. The image selection process was as contentious as the music selection. The team wanted to show what Earth looked like: mountains, oceans, forests, deserts. They wanted to show what humans looked like: a diverse range of faces, ages, and cultures. They wanted to show what we had built: cities, roads, buildings, machines. And they wanted to show what we had learned: diagrams of DNA, mathematical equations, the structure of the solar system. a map showing Earth's location relative to nearby pulsars, using the same technique that had been included on the earlier Pioneer plaques. The final set of images included a picture of a fetus in the womb, a man and woman holding hands, a family group, a classroom full of children, the Great Wall of China, the Taj Mahal, the Sydney Opera House, a diagram of human anatomy. A page from Isaac Newton's Principia Mathematica. The images were not meant to be comprehensive, they were meant to be evocative, to give whoever found the record a sense of what it meant to be human. The greetings were the most personal part of the record. 55 separate audio clips, each one a short message in a different language, recorded by native speakers and compiled into a single track. The greetings ranged from formal to casual, from ancient languages like Sumerian and Sanskrit to modern languages like Mandarin and Spanish. The English greeting, recorded by then Secretary-General of the United Nations Kurt Waldheim, was straightforward. We step out of our solar system into the universe seeking only peace and friendship, to teach if we are called upon, to be taught if we are fortunate. The Mandarin greeting was more poetic. Hope everyone's well. We are thinking about you all. Please come here to visit when you have time. The languages represented every continent, every major culture, and several that were in danger of disappearing. The greetings were a snapshot of linguistic diversity, a reminder that humanity was not a single monolithic entity but a collection of thousands of distinct groups, each with its own way of seeing the world and expressing that vision through language. The cover of the record was a masterpiece of minimalist design. The disc itself was encased in a protective aluminum jacket, and the jacket was engraved with diagrams explaining how to play the record and decode the images. The instructions assumed no prior knowledge of human technology. They started with the basics. The top left corner of the cover showed a diagram of the record itself, with an arrow indicating the direction of rotation. Next to that was a side view showing how to position a stylus, the needle that would read the grooves. Below that was a binary representation of the playback speed, defined using the frequency of a hydrogen atom's electron transition as a universal constant. If an alien civilization had any understanding of physics, they would recognize that frequency and be able to calculate the correct speed. The rest of the cover was filled with diagrams explaining the image encoding scheme, a representation of the solar system showing Earth's position, and the pulsar map indicating where the record had come from. Every element of the design was chosen to be as universal as possible, relying on mathematics and physics rather than cultural assumptions. Frank Drake, the astronomer who had helped design the pulsar map on the Pioneer plaques, was brought in to refine the cover's diagrams. Drake was known for his work on the Drake equation, a formula that estimated the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. He understood better than most people that the odds of the record ever being found were vanishingly small. But he also understood that the act of creating the record mattered as much as whether it was ever discovered. The golden record was not really a message to aliens, it was a message to ourselves, a declaration that humanity believed the universe was worth reaching out to, even if the gesture was symbolic. Drake spent days refining the diagrams, testing them on colleagues, making sure they were as clear and unambiguous as possible. He later said that designing the cover was one of the most difficult communication challenges he had ever faced because he had to think like someone who had never seen a phonograph, never heard music, and never encountered any artifact of human civilization. Every assumption had to be questioned. Every symbol had to be justified. The decision to make the record out of gold-plated copper was both practical and symbolic. Copper was durable, resistant to the vacuum of space and the temperature extremes Voyager would encounter. The gold plating protected the copper from oxidation and added an extra layer of longevity. The disk was designed to last 1 billion years or more, longer than human civilization had existed, longer than most stars would continue burning. The gold also carried symbolic weight. Gold was valuable, rare, associated with permanence and importance in almost every human culture. Plating the record in gold was a way of saying this matters, this is not disposable, this is meant to endure. The team knew that even if the record survived for 1 billion years, the odds of it being found were still close to zero. Voyager was heading toward the constellation Ophiuchus, moving at about 38,000 miles per hour relative to the Sun. At that speed, it would take 40,000 years to come within a few light years of the nearest star in that direction. And even then, the odds of passing close enough to a planet for anyone to notice the spacecraft were infinitesimal. But the record was not built for practicality. It was built for hope. Carl Sagan talked about the golden record in interviews throughout the 1980s and 90s, and he always came back to the same idea. The record was a message in a bottle. Not a message to a specific recipient, but a message cast into the cosmic ocean with no expectation that it would ever be read. The act of sending it was the point. Humanity in 1977 was capable of building machines that could leave the solar system and travel into interstellar space. We were capable of compiling a record of our achievements, our art, our science, and our diversity. And we were capable of imagining a future where someone, somewhere, might find that record and know that we had been here. The record was a statement of intent. We are explorers, we are curious. We believe the universe is full of wonders, and we want to be part of that story, even if we are just a footnote. There was also a darker subtext to the project that Sagan acknowledged but rarely emphasized. The Cold War was still grinding along in 1977. The threat of nuclear annihilation was real. The possibility that humanity might not survive the century was a topic of serious discussion among scientists and policymakers. The Golden Record was, in part, a time capsule. If humanity destroyed itself, if Earth became uninhabitable, if civilization collapsed and the species went extinct, the record would still be out there, drifting through the galaxy, carrying proof that we had existed. It was a hedge against oblivion, a way of ensuring that even if we failed, even if we could not save ourselves, something of what we had been would survive. That idea was never stated explicitly in the official NASA documentation, but it was there, implicit in every decision the team made. The record was not just a greeting, it was a memorial. The music selections reflected that dual purpose. Some of the pieces were celebratory. Chuck Berry's Johnny Be Good was pure joy, a song about a kid with a guitar and a dream. Other selections were more somber. The Navajo night chant was a prayer, a plea for healing and balance. The Pygmy Girls' initiation song was a rite of passage, a recognition that life involved loss as well as growth. The Beethoven was triumphant in the way that only Beethoven could be, taking darkness and struggle and turning them into something transcendent. The Bach was meditative, intricate, a reminder that beauty could be found in structure and order. Every piece of music on the record told a story, and collectively, those stories added up to something larger. Humanity was messy, contradictory, capable of both great cruelty and great kindness. The record did not shy away from that complexity. It embraced it. Andrewan later revealed a detail about the record that had not been public knowledge at the time. One of the sounds included on the disc, labeled as a human heartbeat, was her heartbeat. She had been in love with Carl Sagan during the compilation process, though they were not yet married, and the team needed a recording of a heartbeat to include on the sound compilation. Druan volunteered. She sat in a recording studio with a microphone pressed against her chest, and her heartbeat was recorded and encoded into the disc. She later described the moment as surreal. Her heartbeat, the rhythm that had accompanied every moment of her life, every thought she had ever had, every emotion she had ever felt, was now traveling through interstellar space at 38,000 miles per hour, farther from Earth than any other human artifact. It was a love letter, she said, not just to Carl, but to the universe, a declaration that we were alive, that we felt things, that we mattered. The philosophical implications of the Golden Record have been debated for decades. Some critics argued that the record was hopelessly anthropocentric, assuming that any alien civilization would interpret sounds and images the way humans do. Others pointed out that the record presented an idealized version of humanity, leaving out the wars, the genocides, the environmental destruction, the suffering that had defined much of human history. The team had made a deliberate choice to emphasize the positive aspects of human civilization, not because they were naive or dishonest, but because they believed the record should represent what humanity aspired to be, not just what it had been. Carl Sagan defended that choice in multiple interviews. He said the record was not meant to be a complete or objective account, it was meant to be a portrait. And portraits, by their nature, are selective. They highlight certain features, downplay others, and aim to capture something essential about the subject that raw data cannot convey. The Golden Record also raised questions about who had the authority to speak for humanity. The team that compiled the record was small, mostly white, mostly American, working within the constraints of a government-funded space program during the Cold War. The languages, music, and images they selected were filtered through their own cultural biases and limitations. The Mandarin greeting was included, but not Cantonese. The Navajo night chant was included, but not a song from any of the hundreds of other Native American tribes. The record included images of humans from multiple ethnicities, but the selection was constrained by what photographs were available and what the team had access to within the 6-week deadline. The result was not a perfect representation of humanity. It was a representation shaped by the people who made it, with all the blind spots and priorities that entailed. Sagan acknowledged this limitation. He said the record was not the definitive statement about humanity. It was a statement, one attempt, made by a small group of people in a specific time and place, to say something meaningful about what it meant to be human. Future generations, if they survived, would have the opportunity to send their own messages. The record has been called the most ambitious art project in human history, not because of its technical complexity, though that was considerable, but because of its intended audience. Most art is created for a specific group of people. A painting hangs in a gallery where certain visitors will see it. A song is played on the radio where certain listeners will hear it. A book is published for readers who share a language and a cultural context. The Golden Record was different. It was created for an audience that might not exist. And if that audience did exist, they might not find the record for millions or billions of years, long after the civilization that created it had vanished. The record was not asking to be understood immediately. It was asking to be found someday by someone, and for that someone to take the time to decode it and consider what it meant. That level of ambition, that willingness to create something knowing you would never see the result, was unprecedented. It was an act of faith in the value of communication itself. 47 years after launch, the Golden Record is now 15 billion miles from Earth, farther than any other human-made object. Voyager 1 crossed the Heliopause in 2012 and entered interstellar space, the region beyond the Sun's influence, where the spacecraft is now surrounded by the thin gas and cosmic rays that fill the space between stars. The record is still there, mounted on the side of the spacecraft, protected by its aluminum cover, untouched by human hands since it was installed in 1977. The gold plating has held up. The grooves are intact. If someone were to find the spacecraft tomorrow and figure out how to play the record, it would still work. The sounds would still be audible. The images would still decode. The message would still be readable. The record was built to last 1 billion years. It has only been traveling for 47. The odds of the record ever being found are still vanishingly small. Voyager is moving through a region of space that is almost incomprehensibly empty. The nearest star in the direction Voyager is heading is not particularly close, and even if the spacecraft passed within a few light years, the odds of an alien civilization noticing a small, cold, dead probe drifting past their star system are essentially zero. Space is too big. Voyager is too small. The universe is full of rocks and debris and frozen objects tumbling through the dark, and there is no reason to think an alien astronomer would distinguish Voyager from any other piece of cosmic junk unless they were specifically looking for it. The record will almost certainly never be played. It will drift through space for millions of years, then billions, outlasting the sun, outlasting the Earth, outlasting every trace of human civilization, until eventually it either collides with something or falls into a star or gets torn apart by tidal forces near a black hole. That is the most likely ending for the golden record. Silent, invisible, forgotten. But the record was never really about being found. It was about being sent. The act of creating the record, the process of deciding what to include and how to present it, forced the team to confront questions that most people never think about. What is humanity? What do we value? What do we want to say about ourselves? If you had 90 minutes of audio and 116 images to represent the entire history of human civilization, what would you choose? Those questions do not have easy answers. The Golden Record team spent 6 weeks arguing about them, and the result was a document that reflected their best attempt to answer those questions honestly. The record was not perfect, it was not complete, but it was sincere. And in a universe that is mostly empty, mostly silent, and mostly indifferent to whether we exist or not, sincerity matters. Carl Sagan died in 1996, 20 years after the Golden Record was launched. He spent the last decades of his life promoting science, writing books, and advocating for space exploration. He never stopped talking about Voyager, never stopped reminding people that the spacecraft and its record were still out there, still traveling, still carrying humanity's message into the void. He once said that the Golden Record was a present to ourselves as much as it was a message to aliens, a reminder that we were capable of thinking beyond our immediate needs, beyond our short-term survival, and imagining a future where someone, somewhere, might care that we had existed. That kind of thinking, he argued, was what made us human, not our intelligence, not our technology. Our ability to imagine ourselves as part of something larger, to reach out across impossible distances and say, we are here and we want to connect. The Golden Record is still traveling, still intact, still carrying its cargo of sounds and images and greetings from a planet that is now 15 billion miles away and receding every second. The spacecraft will eventually run out of power. The instruments will shut down. The transmitter will go silent. Sometime in the late 2030s, Voyager will stop sending data back to Earth, and the mission will officially end, but the record will still be there. Mounted on the side of a dead spacecraft, drifting through interstellar space, untouched and unheard. A message in a bottle, cast into the cosmic ocean with no expectation that it will ever be read. The record is not waiting to be found. It is simply there, a statement, a gesture, a love letter to the universe, written by a species that knew it would never receive a reply but sent the message anyway because the act of reaching out mattered more than the answer. Voyager is carrying that message forward, into the dark, into the future, into a time and place where humanity itself might no longer exist. And when the last human has died, and the last city has crumbled, and the earth has been swallowed by the aging sun, the golden record will still be out there, traveling, enduring, carrying proof that we were here and that we cared. That is not a scientific discovery. That is something else, something harder to quantify but no less real, a declaration that we mattered, that we tried, that we sent our voice into the void and hoped, even knowing the odds, that someone might hear it. The golden record is humanity's longest shot, and it is still flying. The golden record is still out there, traveling, enduring, carrying proof that we were here and that we cared, but the spacecraft carrying it is dying, slowly, inevitably, cell by cell, system by system. Voyager is shutting down, not because it crashed, not because it failed, because after 47 years of operation in the vacuum of space, after traveling 16 billion miles through radiation and cold and the endless dark, the power is finally running out. The plutonium cores in the radioisotope thermoelectric generators are decaying, the way all radioactive material decays, following a half-life curve that cannot be stopped or slowed. The engineers who built Voyager knew this would happen. They calculated the timeline decades ago. They knew that by the mid-2030s, the power output would drop below the minimum threshold needed to run the transmitter. They knew the spacecraft would go silent. What they did not know, what nobody could have predicted, was how hard it would be to let go. Because Voyager is not just a machine, it is a companion, a voice from the edge of the solar system that has been speaking to us, uninterrupted, for nearly half a century. And now that voice is fading, the signal is weakening, the end is coming, and there is nothing anyone can do to stop it. As of early 2025, Voyager 1 was operating on less than 200 watts of power. For context, that is roughly the amount of electricity needed to run 2 old-fashioned incandescent light bulbs. The spacecraft launched with 470 watts. The power has been dropping steadily, predictably, at a rate of about 4 watts per year. The plutonium-238 in the radioisotope thermoelectric generators is decaying, producing less heat, and the thermocouples that convert that heat into electricity are generating less current. The rate of decay is not linear. It follows an exponential curve that flattens over time, but never quite reaches zero. The generators will keep producing some power for centuries, but the amount will eventually drop below what the spacecraft needs to operate. That threshold is approaching, fast. The mission team at the Jet Propulsion Laboratory in Pasadena has been managing this decline for years. They call it power budgeting, a term that makes it sound like they are balancing a checkbook, rather than deciding which parts of a 47-year-old spacecraft to kill in order to keep the rest alive. Every instrument, every heater, every system on Voyager draws power. The transmitter, the component that sends data back to Earth, uses about 30 watts. The high-gain antenna pointing system uses another 20. The onboard computer uses 15. The gyroscopes that keep the spacecraft oriented correctly use 10. Add it all up, and you are already at 75 watts just to maintain basic communication. That leaves a little over 100 watts for everything else. Science instruments, heaters to keep the electronics from freezing, backup systems in case something fails. 100 watts is not much, and it is shrinking every year. The team started shutting down non-essential systems in the early 2000s. The first to go were the redundant systems, the backups that had been built into the spacecraft to protect against failures. Voyager had 2 transmitters, 2 receivers, 2 onboard computers, 2 sets of thrusters. The redundancy was deliberate, designed to keep the mission running even if one component failed. But redundancy is a luxury that costs power. By the mid-2000s, the team had switched off most of the backup systems and was running Voyager on a single set of primary instruments. The backups were still there, dormant, waiting in case of an emergency, but they were not drawing power. That bought a few more years. Then the science instruments started shutting down. In 2007, the team turned off the plasma science instrument, the sensor that had measured the solar wind for 30 years. It had done its job. The solar wind had disappeared after Voyager crossed the Heliopause, and there was nothing left for the instrument to measure. Shutting it down freed up 7 watts. In 2008, the planetary radio astronomy instrument was turned off. Another 7 watts. The ultraviolet spectrometer followed in 2016. The instruments were not broken, they were victims of triage. The mission had to choose between keeping them running and keeping the spacecraft alive. The spacecraft won. By 2020, only 5 of Voyager's original 10 science instruments were still operational. The magnetometer, which measured the strength and direction of magnetic fields, the low-energy charged particle detector, which counted ions and electrons, the cosmic ray subsystem, which detected high-energy particles from outside the solar system, the plasma wave instrument, which measured oscillations in the surrounding plasma, and the high-energy particle detector, which tracked the most energetic cosmic rays. Those 5 instruments were the last survivors, the final witnesses to whatever Voyager encountered as it flew deeper into interstellar space. The team knew they would have to shut more of them down eventually. The only question was which ones to kill first, and how long they could delay the inevitable. The decision-making process was agonizing. Each instrument represented decades of work by scientists who had built it, calibrated it, and spent their careers analyzing its data. Shutting down an instrument was not just a technical decision, it was a human decision. It meant telling a scientist that their life's work was over, that their instrument, the one they had poured years into designing and testing, would never send back another data point. The team held meetings, they ran simulations, they debated the scientific value of each instrument against the power it consumed. The discussions were respectful but blunt. How much does this instrument draw? What is it currently measuring? Could we learn the same thing from a different instrument? Is there any scenario where this data would change our understanding of interstellar space in a meaningful way? The answers determined which instruments lived and which ones died. In December 2023, something unexpected happened. Voyager 1 stopped sending coherent data. The spacecraft was still transmitting. The signal was still reaching Earth. But instead of the usual stream of binary ones and zeros, encoding science measurements and spacecraft status updates, the data arriving at the Deep Space Network antennas looked like garbage, repeating patterns, random noise, nothing that made sense. The team at JPL spent weeks trying to figure out what had gone wrong. Was it the transmitter? Was it the onboard computer? Had radiation finally fried a critical component? The spacecraft was 16 billion miles away. You could not exactly send a repair crew. The only tool the engineers had was the ability to send commands and wait 22.5 hours for the signal to reach Voyager, then another 22.5 hours for the response to come back. Troubleshooting a problem with a 45-hour turnaround time is not easy. It is like trying to debug software on a computer that only responds once every 2 days. The breakthrough came in early 2024 when the team sent a command they called a poke. It was not a technical term, it was exactly what it sounded like. They sent a signal, that essentially asked Voyager to reset one of its onboard memory chips and report back what was stored there. The response that came back 45 hours later was a data dump, a full readout of the chip's contents. The engineers analyzed it and found the problem: a single chip in the flight data subsystem, the component responsible for packaging science data before transmitting it, had failed. The failure was not random. It was caused by radiation, a high-energy particle from deep space that had slammed into the chip and flipped enough bits to corrupt the data it was trying to send. The chip could not be repaired. It was hardware, but the software running on the chip could be rewritten. The team spent months developing a patch, a workaround that rerouted the data through a different part of the spacecraft's memory. In April 2024, they uploaded the patch. It worked. Voyager started sending coherent data again. The mission was saved. For now. But the incident was a warning. Voyager was old. The electronics were degrading. Radiation damage was accumulating. The next failure might not be something the team could patch. It might be a thruster that stopped responding, a transmitter that went silent, a power bus that shorted out. The spacecraft was running on borrowed time, and everyone at JPL knew it. The patched flight data subsystem bought a few more years, but it did not change the long-term trajectory. The power was still dropping. The instruments were still shutting down. The end was still coming. In late 2024, the team made the decision to shut down the cosmic ray subsystem. It was one of the 5 remaining instruments, and it was drawing about 7 watts. The data it was sending back was valuable, sure. It was measuring the flux of high-energy cosmic rays in interstellar space, particles that had been accelerated to nearly the speed of light by supernova explosions and other violent events in the galaxy. But the magnetometer and the low-energy charged particle detector were measuring related phenomena, and the team decided the cosmic ray data was redundant enough that they could live without it. 7 watts. That was the trade-off. 7 watts in exchange for a few more months of operation for the other instruments. The cosmic ray subsystem was shut down in January 2025. The data stopped. The scientists who had spent decades analyzing cosmic ray measurements from Voyager knew it was coming, but that did not make it easier. The communication challenges were getting worse. Voyager's signal strength had always been faint. The spacecraft transmitted at a power of about 23 watts, roughly the same as a refrigerator light bulb. By the time that signal traveled 16 billion miles through space, it was almost unimaginably weak. The radio waves spread out as they traveled, diluting their energy over a sphere whose surface area grew with the square of the distance. By the time the signal reached Earth, the power per square meter was measured in attawatts, trillionths of a watt. The only reason NASA could detect the signal at all was because of the Deep Space Network, a collection of 3 massive radio antennas positioned around the globe in California, Spain, and Australia. Each antenna was 70 meters across, the size of a football field stood on end, and they were the most sensitive radio receivers on Earth. Even with those antennas, receiving Voyager's signal required locking onto the spacecraft's frequency for hours at a time, filtering out noise and amplifying the signal until it was strong enough to decode. The data rate was 160 bits per second. A single photograph from Voyager took 10 minutes to transmit. A modern smartphone could send the same image in a fraction of a second, but smartphones did not have to send data across 16 billion miles. The latency made communication feel like a conversation in slow motion. Every command sent from Earth took 22.5 hours to reach Voyager. The spacecraft's response took another 22.5 hours to come back. That 45-hour round trip meant that troubleshooting a problem was a multi-day process. Send a command, wait 2 days, see if it worked. If it did not, send another command, wait 2 more days. The delays were maddening, especially during crises like the 2023 data corruption incident, but there was no way around them. The speed of light was the ultimate speed limit, and even light took nearly a day to cover the distance between Voyager and Earth. The engineers at JPL had learned to be patient. They planned their commands days in advance, double-checked everything before transmitting, and accepted that once a command was sent, there was nothing they could do but wait. The spacecraft was on its own for 45 hours. If something went wrong during that window, they would not know until it was too late to fix it. One of the engineers working on Voyager described the spacecraft's status in early 2025 using a metaphor that stuck with everyone who heard it. He said Voyager was like a patient in hospice, not dead, not suffering, but declining slowly and inevitably with no hope of recovery. The team's job was not to cure the spacecraft. It was to keep it comfortable, to manage the decline as gracefully as possible, and to extract every last bit of value from the time that remained. That meant shutting down systems in the right order, prioritizing the transmitter and antenna above everything else, and accepting that the science instruments, the very reason Voyager was built, would have to be sacrificed to keep the spacecraft talking. The goal was no longer to do great science. The goal was to stay connected as long as possible, to keep the signal alive, to make sure that when Voyager finally went silent, it was because there was no other choice. The team estimated that Voyager 1 would run out of power sometime in the early to mid-2030s. The exact year depended on how many instruments they shut down and how much power the transmitter required as the spacecraft continued moving farther from Earth. By 2030, the power output from the radioisotope thermoelectric generators would drop below 150 watts. By 2035, it would be closer to 100. At that point, there would not be enough power to run the transmitter, the antenna pointing system, and the onboard computer simultaneously. The team would have to choose: keep the computer running and lose the ability to communicate, or keep the transmitter running and lose the ability to control the spacecraft. Either way, the mission would end, the last command would be sent, the last data packet would be received, and then silence. When that moment comes, and it will come within the next decade or so, Voyager will not disappear. It will keep flying. The spacecraft will continue moving through interstellar space at 38,000 miles per hour, covering roughly 3 astronomical units per year, drifting farther from the Sun with every passing second. In 40,000 years, Voyager 1 will pass within about 1.5 light-years of a star called Gliese 445 in the constellation Camelopardalis. It will not be close enough for the star's gravity to capture it. It will just drift past, silent and dark, a frozen artifact from a civilization that by then might not even exist anymore. The golden record will still be there, untouched, unplayed, carrying its cargo of sounds and images into a future so distant it defies comprehension. Voyager will keep traveling for millions of years, billions, until something ends the journey: a collision with a rock, a slow spiral into a star, the gradual erosion of its structure by interstellar dust. Eventually, the spacecraft will be destroyed, but not soon. Not for a very long time. The legacy Voyager leaves behind is not measured in distance. It is measured in what it taught us. Before Voyager, the outer solar system was a collection of guesses and models. After Voyager, it was real. We knew what Jupiter's storms looked like up close. We knew Saturn's rings were made of ice particles ranging from dust grains to boulders. We knew Titan had a thick atmosphere and lakes of liquid methane. We knew Io was the most volcanically active body in the solar system. We knew Europa had an ocean beneath its ice. We knew Uranus was tipped on its side with a magnetic field that did not align with its rotation axis. We knew Neptune had the fastest winds ever recorded on any planet. All of that knowledge came from Voyager. 2 spacecraft, 5 years, 4 planets, and a data return that rewrote every textbook on planetary science. But the real legacy came later. The Heliopause crossing, the discovery of the magnetic highways, the measurement of the interstellar medium's density and temperature, the detection of solar tsunamis propagating beyond the edge of the solar system. Those discoveries were not part of the original mission. They were bonuses, unexpected gifts from a spacecraft that refused to die. Voyager flew farther and lasted longer than anyone predicted, and in doing so, it gave humanity its first direct measurements of the space between stars. We had been guessing about the interstellar medium for a century. Voyager stopped the guessing. It went there, sampled the plasma, measured the magnetic field, recorded the hum, and sent the data home. No model, no matter how sophisticated, could replace that. Voyager was ground truth. And ground truth is the foundation every theory is built on. The mission also changed how scientists thought about exploration. Voyager was designed in the 1970s using technology that was obsolete by the time the spacecraft reached Jupiter. The onboard computer had less memory than a digital watch. The cameras used Vidicon tubes. The data rate was slower than a 1990s dial-up modem. And yet the spacecraft kept working. It adapted. The engineers reprogrammed it in flight, uploading new software to compensate for aging hardware, rerouting data through backup systems, shutting down instruments to conserve power. Voyager survived because the people who built it had designed it to be flexible. They had assumed things would go wrong and had built in enough redundancy and reprogrammability to deal with failures they could not predict. That design philosophy became a model for every deep space mission that followed. Build it tough. Build it smart. Build it to last longer than you think it will need to. NASA is planning a follow-up mission called the Interstellar Probe. The concept is still in the early stages, but the goal is clear. Build a spacecraft specifically designed to travel into interstellar space faster and farther than Voyager ever could, and equipped with instruments tailored to study the heliosphere and the interstellar medium in detail. The Interstellar Probe would launch sometime in the 2030s, assuming funding and political support hold up, and it would use a gravity assist from Jupiter to reach speeds of around 30 to 40 miles per second. That is fast enough to cross the Heliopause in less than 15 years and reach 500 astronomical units, more than 4 times Voyager's current distance, within 50 years. The mission would carry modern instruments, digital cameras, advanced magnetometers, plasma sensors capable of measuring densities far lower than Voyager could detect, and a nuclear power system that would last decades longer than Voyager's radioisotope generators. It would be Voyager's successor, built with everything we learned from 47 years of operation at the edge of the solar system. But even if the Interstellar Probe launches and succeeds, it will not replace Voyager. Voyager was not just a mission, it was a cultural moment. The golden record, the images of Jupiter's great red spot, the pale blue dot photograph taken from the edge of the solar system showing Earth as a tiny speck suspended in a sunbeam. Carl Sagan standing in front of a model of Voyager, explaining to millions of people why exploration mattered. The mission captured something larger than science. It captured the human need to reach beyond ourselves, to see what is over the next hill, even when we know the journey is dangerous and the odds of success are low. Voyager was a bet on the future, a belief that going farther, learning more, and pushing the boundaries of what was possible was worth the cost. That belief is still there. It is what drives every space mission, every telescope, every rover sent to another world. Voyager proved it was possible, and 47 years later, the spacecraft is still out there, still proving it. The final data Voyager sends back will not be dramatic. There will be no grand discovery in the last transmission, no shocking revelation in the final data packet. The spacecraft will keep measuring the same things it has been measuring for years: magnetic field strength, plasma density, cosmic ray flux. The numbers will update. The graphs will shift slightly. And then one day, the signal will stop. Not because Voyager broke, because it ran out of power. The transmitter will shut down, the data stream will end, and the mission control room at JPL, the room where engineers have been listening to Voyager's signal for nearly half a century, will go quiet. The last beep will fade, the last data point will be recorded, and Voyager will drift on in silence, a ghost ship traveling through the dark, carrying the memory of the civilization that built it into a future it will never see. But that has not happened yet. As of early 2025, Voyager is still transmitting, still flying, still speaking to us across 16 billion miles of empty space. The signal is faint, the power is fading, the instruments are shutting down one by one. But the spacecraft is still there, still functional, still doing what it was built to do. And as long as the signal keeps coming, as long as the engineers at JPL can lock onto that faint carrier wave and decode the data buried in the noise, Voyager is alive, not in the biological sense. Machines do not live and die the way organisms do. But in the sense that matters, Voyager is still connected. Still part of the conversation, still a voice from the edge of the known universe, telling us what it sees. There is something profoundly human about that, about the refusal to let go, about the engineers who spend their days managing the decline of a 47-year-old spacecraft, squeezing every last watt out of decaying power systems, rewriting software to work around broken hardware, and doing everything they can to keep the mission alive for one more year, one more month, one more day. They know how this ends. They have known since 1977. The spacecraft will die. The signal will fade. The mission will end. But knowing the ending does not make it easier, because Voyager is not just data, it is not just a machine, it is a companion, a presence, a reminder that we are capable of building things that outlast us, that we can send our creations into the cosmos and they will keep working long after we are gone, that we are in some small way immortal. The fading signal is not a tragedy, it is a completion. Voyager did what it was built to do. It flew farther than any spacecraft before or since. It crossed the boundary between the solar system and the galaxy. It measured things no human had ever measured. It sent back data that changed how we understand the universe. And it carried a message, the golden record, into interstellar space, where it will drift for billions of years, a monument to the idea that humanity was here and we mattered. That is not failure, that is success. The fact that the spacecraft is running out of power does not diminish what it accomplished. It proves it. Voyager lasted 47 years. It was designed to last 5. It beat its design life by more than 9 times. That is not dying. That is winning. The engineers at JPL have a saying: Voyager is not broken, it is just old. There is a difference. Broken things fail because they were not built well enough. Old things fail because they have been running too long. Voyager is old, and when it finally goes silent, it will not be because it failed. It will be because it succeeded. Because it flew so far and lasted so long that the universe itself wore it down. That is the best possible ending for any machine. To run until there is nothing left. To give everything it has. to die not from weakness but from exhaustion, from having done too much, traveled too far, seen too much to keep going. Voyager is exhausted, and it has earned its rest. When the final transmission arrives, and it will arrive sometime in the next decade, it will not be marked with fanfare. There will be no countdown, no live broadcast, no press conference. The signal will simply stop. The last data packet will be decoded. The last science measurement will be recorded. And the deep space network antennas will swing away, pointing toward other missions, other spacecraft, other voices from the cosmos. Voyager will still be out there, still traveling, but we will not hear it anymore. The conversation will be over, and the spacecraft will drift on alone, carrying the golden record into a future so distant and so vast that no human mind can truly comprehend it. The record will outlast the mission. It will outlast the spacecraft. It will outlast the Earth. And billions of years from now, when the sun has burned out and the solar system has dissolved into the expanding remnants of a red giant, the golden record will still be out there, traveling, enduring, carrying proof that humanity existed and that we tried to reach beyond ourselves. That is Voyager's legacy. Not the science, not the data, the gesture, the message, the refusal to accept that the universe is too big and we are too small to matter. We built a machine, we sent it into the dark, and we told it to speak for us. And for 47 years it has. The signal is fading, but it is not gone. Not yet. Voyager is still there, still flying, still whispering across the void. And as long as we can hear it, as long as that faint carrier wave keeps reaching Earth, we are not alone. We are connected to a machine, to a mission, to a moment in history when humanity looked at the stars and said, "We are going there." And we did. Voyager proved it. And when the signal finally fades, when the last transmission ends and the spacecraft falls silent, the proof will remain, carried on a golden disk, traveling through the dark forever. The spacecraft is still flying. That matters more than you might think. Somewhere right now, 16 billion miles from the chair you are sitting in, a machine the size of a small car is cutting through interstellar space at 38,000 miles per hour. It has been flying for 47 years. It will keep flying for millions. The power is fading. The instruments are dying. The transmitter will go silent within a decade, but the golden record is still there, mounted on the side, untouched, waiting. We built Voyager to answer questions about Jupiter and Saturn, to take pictures, to measure magnetic fields, to last 5 years and then disappear. It did all of that in the first decade. Everything since has been a gift. The Heliopause crossing, the magnetic highways, the plasma hum, the solar tsunamis rolling through interstellar space, the direct measurement of a region we had only guessed at for a century. Voyager gave us ground truth. It gave us proof that the models were wrong and the universe was stranger. And it did all of that using technology from the 1970s, running on less power than a refrigerator bulb, transmitting data slower than a modem from the 90s. The spacecraft succeeded not because it was advanced. It succeeded because it refused to quit. There is a lesson in that. Not about engineering, about persistence. About what happens when you build something tough enough to survive and flexible enough to adapt, and you send it into a place where no one can fix it, and it just keeps working. Voyager is dying now, slowly, gracefully, but it is not dead, not yet. The signal is still there, faint, weak, but real, and as long as we can hear it, as long as that carrier wave keeps crawling across 16 billion miles of empty space to reach us, we are connected to the farthest